Imagine a night sky filled with countless stars, tiny pinpricks of light scattered across the endless canvas of space, each one a blazing furnace, burning for millions, billions, or even trillions of years. They seem so small from where we stand, so distant, so peaceful. But they are not small, they are not peaceful, they are cosmic titans, giants beyond comprehension, monsters that defy our very understanding of size and power. Tonight, we journey into the realm of the stars. Not just any stars, but the largest stars ever discovered, the Hypergiants, the stellar leviathans that make our own sun look like a grain of sand beside a mountain. The biggest of them all, a star so vast that if placed where our sun sits, would engulf the orbit of Saturn. A star so enormous that light takes hours to cross from one side to the other. A star whose very existence challenges what we thought possible in our universe. Welcome to a gentle exploration of the most terrifying objects in the cosmos. The biggest stars ever found. As you listen, allow yourself to drift, to float in the cosmic ocean alongside these giants. Feel the warmth of their glow, yet know you are safe, billions of kilometers away from their scorching fury. The human mind was not built to truly comprehend the scale we will discuss tonight. Our brains evolved on a small planet, dealing with sizes we could see and touch. A tall tree, a mountain, an ocean. But the cosmos operates on a scale so vast that we must use analogies, comparisons, and metaphors to even begin to grasp it. So as we talk about stars that could swallow our entire solar system, remember that feeling of smallness is natural. That sense of cosmic vertigo, when contemplating such immensity, is to be expected. There is a certain comfort in knowing our limitations, in accepting that some things are simply too big for us to fully understand. And yet, we try, through science, through mathematics, through powerful telescopes, and clever observations, we reach out across the light years to measure these behemoths, to catalogue them, to understand them, and in doing so, we connect with something greater than ourselves. Tonight's journey will take us from the birth of these stellar giants in cold, dark nebulae, through their brilliant but brief lives, to their spectacular, universe-altering deaths. We will explore how astronomers discovered them, how we measure their mind-boggling dimensions, and what their existence means for the cosmos at large. These stars forge the elements that make up our world. Their tremendous energies shape the galaxies they inhabit, and when they die, they seed the universe with the building blocks of future stars, planets, and perhaps even life. So settle in, relax, allow your mind to expand beyond Earth, beyond our solar system, beyond what seems possible. Together, we will contemplate the greatest giants the universe has to offer. The night sky awaits us, the stars are calling, and the biggest of them all has a story to tell. A story of cosmic fire and celestial majesty, a story of unimaginable power and inevitable decay, a story that begins in the cold darkness of space and ends in an explosion that outshines entire galaxies. This is the story of the biggest stars ever found. The titans of the sky, the monsters that burn so bright they can be seen across millions of light years, the giants whose very heartbeats are felt across the cosmos. Listen now as we begin our journey into the realm of the stellar Hypergiants, the most massive, most luminous, most awe-inspiring objects in our universe. And as you listen, perhaps glance upward at the night sky. Those tiny points of light suddenly seem different when you know what they truly are. Distant suns, cosmic furnaces, and among them, hidden from view but revealed by science, the true giants, the stars whose size and power defy imagination. They are out there right now, burning, pulsing, some dying in spectacular fashion, others still in their prime, pouring out more energy in a second than our sun will produce in its entire lifetime. The biggest star ever found, a titan among titans, a monster among monsters, a celestial body so large it makes worlds look like atoms. that is our destination tonight. A gentle journey to the most extreme object in the known universe. When we look up at the night sky, we see stars as mere points of light. From our perspective on Earth, they all appear roughly the same size, tiny, distant. But this is one of the greatest illusions in astronomy. Stars come in a staggering range of sizes, from the smallest red dwarfs barely larger than the planet Jupiter, to hypergiants so enormous they defy comprehension. So what exactly makes a star big? The answer is more complex than you might imagine. In astronomy, a star's size can be measured in several different ways, and each tells us something unique about the nature of these cosmic furnaces. First, there is the star's radius or diameter. This is the physical size of the star, the distance from its center to its visible surface, or from one side to the other. When astronomers talk about the biggest stars in the universe, they are usually referring to stars with the greatest diameter. Then there is the star's mass. This is the total amount of matter contained within the star. Mass determines how strongly gravity pulls inward, which in turn affects how hot and dense the star's core becomes. More massive stars burn hotter and faster, fusing hydrogen into helium at a much greater rate than their smaller cousins. Finally, there is luminosity. This is the total amount of energy a star radiates into space every second. Some stars are incredibly bright despite being relatively small in diameter, while others may be enormous but relatively cool and dim. These three properties, radius, mass, and luminosity, are deeply interconnected, but they don't always increase or decrease together. A star can be physically enormous, yet contain less mass than a much smaller star. This is one of the great paradoxes of stellar astronomy. To understand why, we need to talk about density. On Earth, we're accustomed to matter being relatively solid and compact. But the matter in stars can be stretched incredibly thin, especially in the largest stars in the universe. Take our Sun as a starting point, an average star by cosmic standards. Our Sun measures about 1.4 million kilometers in diameter. Light takes about 4.5 seconds to travel from one side to the other. The Sun contains enough mass to make 333,000 Earths. It's a cosmic giant from our human perspective. But the Sun is a cosmic dwarf compared to the true giants of the universe. Let's move up the stellar size chart. Beyond ordinary stars like our Sun, we encounter the red giants. These are stars that have exhausted the hydrogen fuel in their cores and have begun to expand dramatically. Our Sun will become a red giant in about 5 billion years, swelling to roughly the size of Earth's orbit. Red giants are typically about 100 times the diameter of our Sun. That means that light would take about 7.5 minutes to cross from one side to the other. At these scales, we're talking about stars that could comfortably fit the orbit of Venus, or even Earth inside them. But red giants are just the beginning of stellar enormity. Beyond red giants, we find the supergiants. These stars begin their lives with much more mass than our Sun, typically 10 to 70 times as much. Because of their greater mass, they burn hotter and evolve faster. When they begin to run out of hydrogen fuel, they expand to become supergiants with diameters anywhere from 30 to 500 times that of our Sun. At the upper end of this range, we're talking about stars so large that they could engulf the orbit of Mars or even Jupiter. Light would take 37.5 minutes to cross from one side to the other of a supergiant 500 times the size of our Sun. These stars are truly enormous, with volumes billions of times greater than our Sun. But even supergiants pale in comparison to the true monsters of the stellar world, the hypergiants. Hypergiants represent the upper extreme of stellar size, with diameters ranging from 700 to over 2,000 times that of our Sun. These cosmic behemoths defy imagination. If you placed a hypergiant where our Sun is, its surface would extend beyond the orbit of Jupiter, possibly reaching Saturn or even Uranus. Light would take hours to travel from one side of a hypergiant to the other. These stars contain volumes trillions of times greater than our Sun. They are among the largest single objects in the universe. Now, here's where things get interesting. Despite their enormous size, hypergiants don't necessarily contain the most mass. In fact, the most massive stars known might be only 20 to 30 times the diameter of our Sun, but contain over 100 times its mass. These stars are incredibly dense compared to hypergiants, which tend to be quite diffuse. This brings us to an important distinction in astronomy. The biggest stars by diameter are not the same as the most massive stars. The most massive stars are typically Wolf-Rayet stars, or blue supergiants, which are extremely hot, bright, and dense. The biggest stars by diameter are typically red hypergiants, which are enormous but relatively cool and diffuse. To understand why this is the case, we need to delve into the physics of stellar structure. Stars exist in a precarious balance between two opposing forces. Gravity constantly pulls all the star's mass inward, trying to make it collapse. Working against gravity is the outward pressure created by the nuclear fusion reactions in the star's core. This is thermal pressure, similar to how a hot air balloon expands because the heated air inside pushes outward. In a stable star like our Sun, these forces are perfectly balanced. The inward pull of gravity exactly matches the outward push of thermal pressure. The star neither collapses nor expands. It maintains a stable size for billions of years. But as a star ages and its core composition changes, this delicate balance shifts. When a star begins to run out of hydrogen fuel in its core, the core contracts and heats up. This increased heat causes the outer layers of the star to expand dramatically. The star swells to many times its original size, becoming a red giant, supergiant, or in extreme cases, a hypergiant. The largest stars in the universe, the red hypergiants, have expanded to such enormous sizes that their outer layers are extremely tenuous. If you could somehow travel to one of these stellar giants and pass through its outer layers, you might not even realize you were inside a star. The matter there is so diffuse that it's more of a superheated fog than what we typically think of as stellar material. This is why hypergiants can be so enormous, yet contain relatively less mass than you might expect. Their matter is spread incredibly thin over a vast volume of space. It's like comparing a dense marble to an enormous cloud of cotton candy. The cotton candy might occupy far more space, but the marble contains more matter in a compact form. So when astronomers talk about the biggest star ever found, they're typically referring to the star with the greatest diameter, not necessarily the greatest mass. Let's explore some specific examples to make this clearer. Betelgeuse is one of the most famous supergiants, visible to the naked eye as the bright red star in the constellation Orion. Betelgeuse has a diameter about 700 to 800 times that of our Sun. If placed where our Sun is, its surface would extend beyond the orbit of Mars, almost to Jupiter. Yet Betelgeuse contains only about 15 to 20 times the mass of our Sun. Its enormous volume is filled with relatively diffuse matter. Then there's Antares, another red supergiant visible in our night sky as the heart of the constellation Scorpius. Antares has a diameter around 800 times that of our Sun, but contains only about 12 times the mass. Again, we see this pattern of enormous size but relatively modest mass. Moving up the size scale, we encounter VY Canis Majoris, a red hypergiant in the constellation Canis Major. For many years, it was considered the largest known star, with estimates placing its diameter at 1,500 to 2,000 times that of our Sun. However, more recent measurements have revised its size downwards somewhat. Still, it remains one of the largest stars known, with a diameter perhaps 1,200 times that of our Sun. Despite this enormous size, VY Canis Majoris may contain only about 30 times the mass of our Sun. Then there's UY Scuti, a red supergiant or hypergiant in the constellation Scutum. Current measurements suggest UY Scuti has a diameter about 1,700 times that of our Sun, making it one of the largest stars currently known. If placed at the center of our solar system, its surface would extend beyond the orbit of Jupiter. Yet UY Scuti contains perhaps just 10 to 20 times the mass of our Sun. And finally, the current record holder for the largest known star might be Stephenson 2-18, a red supergiant or hypergiant located in the Stephenson 2 cluster. Some measurements suggest it could have a diameter up to 2,150 times that of our Sun, though this figure is still being debated. If these measurements are correct, Stephenson 2-18 would extend beyond the orbit of Saturn if placed at the center of our solar system. It's worth noting that measuring the exact size of these stellar giants is extremely difficult. They're located thousands of light years away, and their outer boundaries are often ill-defined. The surface of a hypergiant isn't solid like the surface of a planet. Instead, it gradually thins out into space, making the exact boundary somewhat arbitrary. Different methods of measurement can yield different results, and our understanding of these cosmic monsters continues to evolve as our observational techniques improve. But regardless of the exact numbers, the scale of these objects is truly astounding. We're talking about single stars that could engulf much of our solar system. Stars so large that light takes hours to cross from one side to the other. Stars whose volumes could contain trillions of copies of our Sun. Yet size isn't everything in the stellar world. Some of the most extreme stars are not the largest by diameter, but the most massive or the most luminous. For example, R136A1, a star in the Tarantula Nebula, may contain up to 300 times the mass of our Sun, making it possibly the most massive star currently known. Despite this enormous mass, its diameter might be only 30 to 40 times that of our Sun. R136A1 is incredibly dense compared to the Hypergeans, and it shines with the brightness of several million suns. Similarly, stars like Eta Carinae and the Pistol Star are not the largest in diameter, but are among the most luminous stars known, each shining with the light of several million suns. These stars aren't big in terms of physical size, but they're giants in terms of energy output. This brings us to an important point about stellar classification. Astronomers categorize stars not just by size, but by their spectral characteristics, which relate to temperature, and by their luminosity class, which relates to brightness. The spectral classification, from hottest to coolest, uses the letters O, B, A, F, G, K, and M. Our Sun is a G-type star, relatively cool compared to the fierce blue O and B stars, but hotter than the cool red K and M stars. The luminosity classification uses Roman numerals, with I for supergiants, 3 for giants, and V for main sequence stars, like our Sun. Hypergiants sometimes get the designation 0 or Ia+, to indicate their extreme luminosity. So, when we talk about the biggest stars in the universe, we're typically referring to M or K-type supergiants or hypergiants, classes I or 0. These are cool, red stars that have expanded to enormous sizes. The fascinating thing about these stellar classifications is that they tell a story. Stars aren't born as hypergiants, they evolve into them. A star like UY Scuti or Stephenson 2-18 wasn't always so enormous. It began its life as a hot, blue, massive star, perhaps 100 times the mass of our Sun, but relatively compact. Over millions of years, as it aged and its core evolved, it expanded to its current enormous size. This evolutionary journey is a key part of understanding what makes certain stars so incredibly large. It's not just about how much mass they have, but about what stage of life they're in. The biggest stars are typically nearing the end of their lives. They've swollen to enormous sizes as they struggle to maintain equilibrium with changing core conditions. And this leads us to another crucial point about stellar giants. They are rare and short-lived. The universe simply doesn't produce many stars massive enough to become hypergiants, and those that do form live for only a few million years before exploding as supernovae. Our Sun, by comparison, will live for about 10 billion years. The rarity of these stellar monsters makes them all the more precious to astronomers. Each one is a laboratory for studying extreme physics, a window into processes that can't be replicated on Earth. But their scientific value isn't the only reason they captivate us. There's something deeply awe-inspiring about contemplating objects of such immense scale. Standing on Earth, looking up at the night sky, it's hard to imagine that some of those tiny points of light are stars so vast they could swallow our entire solar system. The largest stars remind us of the incredible diversity of cosmic objects and the extreme conditions that exist in our universe. They stretch our imagination and challenge our understanding of what's possible in nature. And they raise intriguing questions. How large can a star get before it becomes unstable? Is there a theoretical maximum size for a star? Could stars even larger than Stephenson 2-18 exist in distant corners of the universe, yet to be discovered? Current astrophysical models suggest there probably is an upper limit to stellar size, likely not much larger than the hypergiants we've already found. As a star expands beyond a certain point, its gravitational hold on its outer layers becomes so tenuous that they simply drift away into space. The star begins to lose mass through powerful stellar winds, preventing it from expanding indefinitely. This process is clearly visible in stars like VY Canis Majoris, which is surrounded by enormous clouds of ejected material. These stars are literally tearing themselves apart as they approach the theoretical limits of stellar size. So while we might discover stars marginally larger than our current record holders, it seems unlikely that we'll find stars dramatically larger than what we already know. The laws of physics impose certain constraints on stellar structure, no matter where in the universe a star forms. But within those constraints, nature has created objects of truly breathtaking scale. The hypergeans represent one extreme of the stellar spectrum, showcasing just how large a single object can become in our universe. As we contemplate these cosmic giants, we're reminded of our own small place in the cosmos. Our entire planet is less than a speck compared to these stellar behemoths. Yet through science and observation, we've managed to reach across the light years to measure and understand them. There's something deeply humbling about this reality. We are tiny beings on a small planet orbiting an average star in an ordinary galaxy. Yet we've developed the knowledge and technology to comprehend objects of such vast scale that they seem to belong to the realm of science fiction rather than science fact. The biggest stars ever found aren't just astronomical curiosities. They're reminders of the incredible diversity of the cosmos and of the boundless capacity of the human mind to explore and understand even the most extreme objects in existence. In our next chapter, we'll delve deeper into the life cycle of these stellar giants, exploring how they form, evolve, and eventually die in spectacular fashion. But for now, simply let the scale of these objects sink in. The largest stars known are so enormous that if placed where our sun is, they would engulf most of our solar system. Their volume could contain trillions of suns. Their light takes hours to travel from one side to the other. These are the true titans of the cosmos, the biggest single objects we can see, monuments to the incredible forces and processes that shape our universe. The journey to understanding the size of stars began centuries ago, with early astronomers who first recognized that stars were distant suns rather than mere points of light in the celestial sphere. But measuring these distant objects presented an enormous challenge. How do you determine the size of something trillions of kilometers away? The breakthrough came with the development of spectroscopy, the study of how matter interacts with electromagnetic radiation. By analyzing the light from stars, astronomers could determine their temperature, and from temperature, they could calculate the amount of energy each square meter of the star's surface was emitting. By comparing this with the star's overall brightness as seen from Earth, they could work out how large the star must be. This technique revealed that stars come in a staggering variety of sizes. Some stars, like the red dwarf Proxima Centauri, our nearest stellar neighbor, are just 1/7 the diameter of our Sun. Others, like the hypergeans we've discussed, are thousands of times larger. When we talk about the concept of bigness in stars, we must also consider time. Stars are not static objects. They change dramatically over their lifetimes. Our Sun will eventually swell to become a red giant before shrinking down to a white dwarf about the size of Earth. The most massive stars undergo even more dramatic transformations, sometimes swelling to become hypergiants before collapsing catastrophically in supernova explosions. This temporal dimension adds another layer of complexity to our understanding of stellar size. The biggest stars are not just physically enormous at a particular moment. They're also rapidly changing, often expanding or contracting at rates that would be noticeable over a human lifetime. Some hypergeans pulsate, growing and shrinking cyclically as waves of energy pulse through their tenuous outer layers. Consider the star VV Cephei. This red hypergeant experiences eclipses as a companion star orbits around it. By carefully timing these eclipses, astronomers have determined that VV Cephei's diameter is approximately 1,600 times that of our Sun. But this figure isn't constant. VV Cephei, like many hypergeants, is unstable, with its outer layers continuously shifting and changing. The distinction between a star's photosphere, the visible surface we can see, and its outer atmosphere often blurs in these giants. Where does the star end and empty space begin? This boundary becomes increasingly difficult to define as we move up the stellar size scale. For stars like UY Scuti or VY Canis Majoris, the transition from star to space is gradual. The density of stellar material decreases steadily with distance from the center, eventually becoming indistinguishable from the surrounding interstellar medium. This makes precise size measurements challenging, and explains why estimates for the same star can vary significantly. Modern astronomers use a variety of techniques to measure stellar sizes. For relatively nearby stars, we can use interferometry, combining light from multiple telescopes to achieve resolution fine enough to directly measure a star's disk. For more distant stars, we rely on indirect methods, inferring size from luminosity, temperature, and other observable properties. The Gaia Space Telescope, launched in 2013, has revolutionized our understanding of stellar properties by providing precise distance measurements to billions of stars. Knowing the exact distance to a star allows astronomers to convert apparent brightness to true luminosity, which combined with temperature gives a reliable estimate of size. But even with these advanced techniques, measuring the largest stars remains challenging. They're rare, often distant, and frequently obscured by dust. The current record holders for largest star might change as measurement techniques improve or as new candidates are discovered. Despite these challenges, what's clear is that the upper limit of stellar size is vastly greater than most people imagine. The sheer scale of the largest stars forces us to confront the limitations of human intuition when dealing with cosmic dimensions. Imagine standing on a planet orbiting at a safe distance from a hypergiant like UY Scuti. Looking up, you wouldn't see a point of light or even a small disk like our sun appears from Earth. Instead, you'd see an enormous red wall of fire filling a large portion of the sky. The star would appear not as a distant object, but as an immense presence, dominating the local space. From such a vantage point, the true scale of these cosmic titans would be unmistakable. You would viscerally understand what is difficult to grasp from Earth, that some stars are so enormous they seem less like objects in space and more like regions of space itself, vast volumes of incandescent plasma held together by gravity. As we continue our exploration of these stellar monsters, we'll delve deeper into how they form and evolve, examining the cosmic processes that create such extreme objects. But the key takeaway from this chapter is simple. Stars come in an astonishing range of sizes, from cosmic dwarfs to unimaginable giants, and the largest among them stretch the very limits of what's physically possible in our universe. The concept of bigness in astronomy extends beyond what we can directly perceive. It challenges us to think in terms of light hours rather than kilometers, volumes measured in trillions of suns rather than cubic meters. It pushes us beyond everyday experience into the realm of mathematical abstraction and theoretical physics. Yet for all their enormity, even the largest stars are dwarfed by the scale of galaxies and the vast cosmic web that structures our universe. They remind us that bigness is relative, and no matter how large an object might seem, there's always something larger to contemplate in the cosmic hierarchy. This sense of scale, this progression from the human to the planetary, to the stellar, to the galactic and beyond, gives us perspective. It helps us locate ourselves within the grand tapestry of existence, tiny yet capable of comprehending the immense. To understand how the biggest stars in the universe come to exist, we must first understand the complete life cycle of stars, from birth to death. This cosmic journey begins in the cold, dark reaches of space and ends, for the largest stars, in some of the most violent events the universe can produce. Our story begins with a cloud, not the kind that brings rain on Earth, but a vast cold cloud of hydrogen and helium gas, mixed with traces of heavier elements, floating in the emptiness between stars. Astronomers call these nebulae, from the Latin word for cloud. Some nebulae are visible from Earth as colorful, wispy structures stretching across light years of space. These cosmic clouds are incredibly tenuous. Their density is far less than even the best vacuum we can create on Earth. If you were somehow able to fly through a nebula, you wouldn't feel anything. You wouldn't even notice it was there without special instruments. Yet despite this extraordinary thinness, nebulae contain enormous amounts of matter spread across vast volumes of space. A typical stellar nursery nebula might contain enough gas to make thousands or even millions of stars. Under normal circumstances, the gas in these clouds remains diffuse, with atoms separated by vast distances compared to their size. But occasionally, something disrupts this equilibrium. Perhaps a shockwave from a distant supernova explosion ripples through the cloud. Maybe the gravitational influence of a passing star creates a disturbance. Or perhaps the cloud drifts into a region of increased cosmic pressure. Whatever the trigger, parts of the cloud begin to condense, This is where the story of every star begins, including the future hypergiants. As gravity pulls the gas molecules closer together, the density increases. With greater density comes more gravitational attraction, pulling even more material inward. A snowball effect ensues, with the center of the condensing region becoming increasingly dense. As the gas falls inward, its gravitational potential energy is converted to heat. The center of the cloud begins to warm up. This nascent star, called a protostar, is not yet hot enough to shine through nuclear fusion, but it glows dully from the heat of gravitational compression. For most stars, this collapse phase lasts a few 100,000 years, a mere blink in cosmic terms. But the future monsters of the stellar world, those that will someday become supergiants and hypergiants, begin their lives with much more mass than ordinary stars. They draw in vast amounts of material from their surroundings, sometimes consuming what could have become several smaller stars. The exact mechanism that creates these stellar titans rather than groups of smaller stars is still not fully understood. It likely involves a combination of factors: the initial density of the cloud, the amount of rotation, the presence of magnetic fields, and perhaps even a bit of cosmic chance. What we do know is that when the dust settles, some protostellar cores have accumulated enough material to eventually become the largest stars in the universe. As the protostar continues to contract, its core temperature rises. When it reaches about 10 million degrees Celsius, something remarkable happens. The heat and pressure become so intense that hydrogen nuclei begin to overcome their natural electromagnetic repulsion and fuse together to form helium. This nuclear fusion releases enormous amounts of energy, and the star truly begins to shine. This moment, the initiation of hydrogen fusion, marks the birth of a proper star. The outward pressure generated by fusion energy finally balances the inward pull of gravity, and the star stabilizes. It has reached what astronomers call the main sequence, the longest and most stable part of a star's life. For a star like our Sun, the main sequence lasts about 10 billion years. But for the most massive stars, those destined to become the giants and hypergiants, this stable period is dramatically shorter. A star with 50 times the mass of our Sun might spend only 4 million years on the main sequence. That's less than 1/10,000th the lifetime of our Sun. This dramatic difference in lifespan comes down to a simple principle. The more massive a star is, the hotter and more compressed its core becomes, and the faster it burns through its hydrogen fuel. These massive stars are like cosmic sports cars, powerful but inefficient, burning through their fuel at a prodigious rate. During their main sequence lifetime, these massive stars shine with an intensity that's difficult to comprehend. A star with 50 times the Sun's mass might be 500,000 times more luminous. The largest stars can outshine entire collections of ordinary stars, visible across immense distances even from other galaxies. But this extravagant energy production cannot last. Eventually, even the most massive stars exhaust the hydrogen in their cores. When this happens, the balance between gravity and fusion pressure shifts, and the star enters a new phase of life. With hydrogen fusion no longer occurring in the core, the outward pressure that had been holding up against gravity diminishes. The core begins to contract under its own weight, growing hotter and denser in the process. Meanwhile, hydrogen fusion continues in a shell around the core, pumping energy into the star's outer layers. This combination of a contracting core and an energetic fusion shell has a dramatic effect on the star's structure. The outer layers begin to expand enormously, cooling as they do so. The star swells to many times its main sequence size, becoming a supergiant. For the most massive stars in the universe, this expansion is truly spectacular. A star that was perhaps 50 times the diameter of our Sun during its main sequence might balloon to hundreds or even thousands of times the Sun's diameter as a supergiant. But the story doesn't end there. Unlike less massive stars, which might remain as stable red giants for billions of years, the evolution of the most massive stars continues at a breakneck pace. As the core continues to contract and heat up, it eventually reaches temperatures of around 100 million degrees Celsius. At this point, helium nuclei begin to fuse into carbon and oxygen. This new source of fusion energy temporarily stabilizes the star, but the helium supply is consumed even faster than the hydrogen was. A star with 50 times the Sun's mass might burn through its core helium in just 500,000 years. Once the helium is exhausted, the process repeats. The core contracts again, heats up further, and begins fusing carbon into heavier elements. Each successive fuel burns faster than the last. Carbon fusion might last just a few hundred years, neon fusion a year or less, oxygen fusion a few months, and silicon fusion only a day. This frantic pace of evolution is unique to the most massive stars. Our Sun, by contrast, will never get hot enough to fuse elements heavier than helium. As these massive stars race through their evolutionary phases, they often become increasingly unstable. Their enormous size works against them. The gravitational pull at their surfaces becomes so weak that material can easily escape, blown away by the intense radiation from within. These stars lose mass at a tremendous rate, shedding material in powerful stellar winds that can be seen across interstellar distances. Some massive stars lose more than half their initial mass during their lifetimes. This material enriches the surrounding space with heavy elements forged in the star's interior, seeding the cosmos with the building blocks for future generations of stars and planets. The most extreme examples of this mass loss occur in stars that become luminous blue variables, or Wolf-Rayet stars, stages that often precede or accompany the hypergeant phase. These stars experience violent eruptions, sometimes ejecting entire suns' worth of material in a single event. The star Eta Carinae is a prime example. In the 1840s, it briefly became the second brightest star in Earth's night sky, despite being over 7,000 light-years away. This event, known as the Great Eruption, ejected more than 10 times the mass of our Sun into space, creating the beautiful bipolar nebula we can see today. These eruptive phases contribute to the enormous apparent size of hypergeants. The star itself may be surrounded by shells or clouds of ejected material that make it difficult to determine where the star ends and the surrounding nebula begins. As massive stars approach the end of their lives, they develop a distinctive onion-like structure. At the center is an iron core, surrounded by layers of silicon, oxygen, neon, carbon, helium, and hydrogen. Each layer is the site of ongoing fusion reactions, creating a series of concentric fusion shells. This structure is fundamentally unstable. Iron represents the end of profitable fusion. Fusing elements lighter than iron releases energy, but fusing iron or heavier elements consumes energy. Once a massive star develops an iron core, its fate is sealed. The iron core continues to grow as the overlying silicon layer fuses to produce more iron, but without fusion energy being generated in the core, there's nothing to counteract the crushing force of gravity. When the iron core reaches about 1.4 times the mass of our Sun, electron degeneracy pressure, the quantum mechanical effect that had been supporting the core, suddenly fails. What happens next occurs with shocking rapidity. The core collapses from a size of a few thousand kilometers to just a few tens of kilometers in less than a second. The inner core becomes so dense that protons and electrons are forced to combine, forming neutrons. The outer layers of the star, suddenly finding nothing supporting them, fall inward at speeds reaching 23% of the speed of light. When these falling layers hit the newly formed neutron core, they bounce, creating a shock wave that races outward. Aided by a flood of neutrinos from the collapsing core, this shock wave tears through the star and bursts out into space. The star explodes as a supernova, briefly shining as brightly as billions of suns. The fate of the stellar core depends on its mass. If the collapsing core is less than about 3 times the mass of our Sun, it will stabilize as a neutron star, an object so dense that a teaspoon of its material would weigh billions of tons on Earth. If the core is more massive, not even neutron degeneracy pressure can halt the collapse, and a black hole forms, an object so dense that not even light can escape its gravitational pull. The supernovae of the most massive stars are among the most energetic events in the universe. They can outshine entire galaxies for a brief period, and their light can be seen across cosmic distances. These explosions scatter the heavy elements forged in the star's interior across interstellar space, enriching the galaxy with the raw materials for future stars, planets, and eventually, life. This, then, is the life cycle of the most massive stars in the universe. From humble beginnings in cold gas clouds, they accumulate enormous amounts of matter, shine with the brightness of millions of suns, expand to become some of the largest single objects in the universe, and end their lives in spectacular explosions that seed the cosmos with heavy elements. But this general outline doesn't capture the full complexity and diversity of massive stellar evolution. Factors like initial mass, chemical composition, rotation rate, and the presence of companion stars can all significantly affect how a particular star evolves. For example, rapidly rotating massive stars can experience enhanced mixing between their core and envelope, altering their evolutionary path. Stars in binary systems can exchange mass with their companions, gaining or losing material in ways that dramatically affect their fate. And not all massive stars follow the neat progression from main sequence to supergiant to supernova. Some may experience episodes as luminous blue variables, Wolf-Rayet stars, or other exotic types at various points in their evolution. The hypergiants, those stars at the very upper end of the size scale, represent extreme cases in stellar evolution. Their enormous size and tenuous outer layers make them inherently unstable. They exist on the edge of what's physically possible for a star, constantly battling against their own gravity and radiation pressure. These stars exhibit a variety of unusual behaviors. Some pulsate dramatically, changing in brightness and size over periods of months or years. Others experience sudden outbursts, ejecting shells of material that form complex nebulae around the star. A few, like the aforementioned Eta Carinae, undergo major eruptions that rival supernovae in energy but leave the star intact. The hypergiant VY Canis Majoris is surrounded by one of the most complex nebulae ever observed around a single star, composed of multiple arcs, knots, and filaments of ejected material. These structures tell the story of numerous mass loss events occurring over thousands of years, each ejecting material in different directions. Similarly, the red hypergiant NML Cygni is losing mass so rapidly that it's surrounded by a circumstellar envelope expanding outward at 20 kilometers per second. This material forms a nebula that extends tens of thousands of astronomical units from the star. These mass loss events are crucial to understanding the true size of hypergiants. When astronomers attempt to measure the diameter of such stars, they must contend with the question of where the star ends and the surrounding nebula begins. Different observational techniques may yield different answers, depending on how they define the star's boundary. But regardless of the exact measurements, what's clear is that the life cycle of the most massive stars proceeds at a dramatically accelerated pace compared to stars like our Sun. While our Sun will shine steadily for about 10 billion years before becoming a red giant, a 50 solar mass star might exhaust its hydrogen fuel in just 4 million years and proceed through its giant and supergiant phases in mere thousands of years. This rapid evolution has important implications for our understanding of the cosmos. The most massive stars, despite their rarity, have a disproportionate impact on their surroundings. Their intense radiation ionizes nearby gas, their powerful stellar winds sculpt the interstellar medium, and their final supernovae explosions trigger new rounds of star formation. In a very real sense, these cosmic monsters drive the evolution of entire galaxies. They're the engines that process primordial hydrogen and helium into the heavier elements needed for planets and life. Without the short, violent lives of massive stars, the universe would be a far less interesting place. As we conclude our exploration of stellar life cycles, it's worth reflecting on the vast difference between cosmic and human timescales. Even the brief lives of massive stars unfold over millions of years. The expansion that transforms a main sequence star into a supergiant or hypergiant occurs over thousands of years. These processes are so slow by human standards that we never see them happen in real time. Instead, astronomers piece together the life cycles of stars by observing many different stars at different stages of evolution, like assembling a film from random frames. The picture that emerges is one of constant change and eventual destruction, a reminder that even the most massive objects in the universe are transient on cosmic timescales. The hypergiants we observe today are merely the current record holders in an ongoing cosmic competition. Millions of years ago, different stars held the title of biggest or most massive. Millions of years from now, the current champions will be long gone, having exploded as supernovae, while new giants take their place. This constant renewal is the true story of stars. They are not eternal, unchanging points of light, but dynamic entities with births, lives, and deaths. The largest among them live fast and die young, their brief cosmic lives burning with an intensity that outshines billions of smaller stars combined. In the next chapter, we'll explore in more detail just how large these stellar monsters can get, examining the current record holders for the biggest stars in the universe and trying to comprehend their truly staggering scale. The role of magnetism in stellar evolution is another fascinating aspect of these cosmic giants. Massive stars generate powerful magnetic fields through the complex movements of charged plasma in their interiors. These magnetic fields can reach strengths thousands of times greater than Earth's magnetic field, and they play crucial roles in shaping the star's behavior. When a massive star rotates, its magnetic field can channel stellar wind outflows, creating structured patterns in the surrounding nebula. We see evidence of this in the complex, often bipolar shapes of the nebulae surrounding many hypergiants. The magnetic fields can also transfer angular momentum from the star's core to its outer layers, affecting how quickly different parts of the star rotate. This differential rotation has profound implications for stellar evolution. Parts of the star rotating at different speeds create shear forces that mix material between layers, bringing fresh hydrogen into the core and carrying fusion products outward. This mixing can extend a star's lifespan and alter its chemical evolution. For the most massive stars, another factor comes into play: their intense radiation pressure. These stars produce so much light and other electromagnetic radiation that the outward push of photons becomes a significant force in their structure. In the outer layers of hypergiants, radiation pressure can exceed gas pressure as the main force opposing gravity. This radiation-dominated structure creates instabilities. Regions of slightly higher density absorb more radiation, heat up, expand, and then become more transparent, creating a pulsation mechanism. Many hypergiants show evidence of such pulsations, varying in brightness over periods ranging from months to years. The most extreme manifestation of radiation pressure effects is found in stars approaching what astronomers call the Eddington limit. This theoretical limit represents the point where the outward force of radiation exactly balances the inward pull of gravity. Stars near this limit become highly unstable, prone to massive eruptions as they struggle to maintain equilibrium. The hypergiant Eta Carinae, which we mentioned earlier, appears to have exceeded the Eddington limit during its great eruption in the 1840s. For a brief period, it was releasing energy at a rate that its gravitational pull couldn't contain, resulting in the ejection of enormous amounts of material. This interplay between gravity, radiation pressure, and other forces creates a delicate balance in hypergiants. They exist at the edge of stellar stability, constantly adjusting their structure to maintain equilibrium. When that balance fails, as it inevitably must, the results can be spectacular. Another fascinating aspect of massive stellar evolution is the role of episodic mass loss. Rather than losing material at a steady rate, many hypergiants experience distinct episodes of enhanced mass loss, sometimes ejecting several solar masses of material in a single event. These episodic ejections create the spectacular nebulae we observe around many hypergiants. The nebula surrounding VY Canis Majoris shows evidence of multiple ejection events occurring over hundreds of years. Each eruption sends material outward at different angles and velocities, creating the complex structure we see today. The mechanism behind these eruptions remains incompletely understood. They may result from pulsational instabilities in the star's outer layers, sudden changes in nuclear burning rates in the core, or interactions with companion stars. Whatever the cause, they represent moments when the star temporarily loses its struggle against its own enormous size and power. For stars nearing the end of their lives, these mass loss events become increasingly frequent and powerful. The star gradually sheds its outer layers, revealing hotter layers beneath. This process can transform a cool red hypergiant into a hotter yellow or blue hypergiant, or even a Wolf-Rayet star with a surface temperature of over 50,000 degrees Celsius. This evolutionary journey across the Hertzsprung-Russell diagram, the chart astronomers use to classify stars by temperature and luminosity, occurs much more rapidly for massive stars than for their smaller counterparts. A star with 50 times the Sun's mass might traverse the entire diagram in just a few thousand years, a cosmic eye blink. The final stages of a massive star's life involve increasingly desperate attempts to stave off collapse. As each nuclear fuel is exhausted, the core contracts and heats up until the next fusion process can begin. But each successive fuel burns faster than the last, accelerating the star toward its inevitable end. During these final stages, the star's structure becomes increasingly complex and dynamic. The multiple fusion shells create regions of different density and temperature, leading to convective mixing that can bring freshly synthesized elements to the surface. Astronomers can detect this mixing through spectroscopic observations. The surfaces of many evolved massive stars show abundances of heavy elements that could only have been created in their deep interiors. These elements, brought to the surface by convection, are then spread into space through stellar winds and eruptions. This process of nucleosynthesis and ejection is one of the most important roles massive stars play in cosmic evolution. Elements like carbon, oxygen, silicon, and iron, essential for planets and life, are created inside massive stars and distributed through space when the stars die. The most massive stars can produce elements all the way up to iron in their cores through nuclear fusion, but the creation of even heavier elements requires the extreme conditions of a supernova explosion. In the fleeting moments of a core collapse, temperatures can reach billions of degrees, allowing for the rapid neutron capture process that creates gold, platinum, uranium, and other heavy elements. This means that quite literally, the gold in your jewelry, the iron in your blood, and the oxygen you breathe were all forged inside massive stars that lived and died billions of years ago. We are, in a very real sense, made of stardust, specifically dust from ancient stellar giants. The final moments of a massive star's life are perhaps the most dramatic. As the iron core grows to a critical mass, electron degeneracy pressure can no longer support it against gravity. The core collapses from a size similar to Earth to that of a city in less than a second, reaching densities where atomic nuclei are essentially touching. This collapse liberates an enormous amount of gravitational potential energy, most of which is carried away by neutrinos, ghostly particles that barely interact with normal matter. But a small fraction of this energy is transferred to the star's outer layers through processes that are still not fully understood, creating the supernova shockwave. For stars above about 100 times the Sun's mass, an even more extreme fate may await. Instead of a conventional supernova, they may experience a pair instability supernova. In this process, temperatures in the core become so high that gamma rays spontaneously convert into electron-positron pairs, reducing pressure support and triggering a catastrophic collapse. The resulting explosion can completely disrupt the star, leaving no remnant behind. Alternatively, for stars above roughly 240 solar masses, the collapse may be so powerful that it creates a black hole directly, without a visible supernova at all. These most massive stars are exceedingly rare, and astronomers are still searching for definitive examples and evidence of their unique evolutionary paths. But theoretical models suggest they must exist, at least in the early universe when stars formed from nearly pure hydrogen and helium. The study of massive stellar evolution continues to advance with new observations and more sophisticated computer models. Each improvement in our understanding reveals additional complexity in the lives of these cosmic titans. One area of active research involves the role of binary interactions. Most massive stars are born in multiple systems, often in close orbits with other massive stars. These companions can dramatically alter a star's evolution through tidal forces, mass transfer, or even mergers. Some of the largest stars we observe today may be the products of stellar mergers, where two massive stars in a binary system spiral together to form a single, even more massive object. This mechanism might explain the existence of stars that seem too massive for their environments or ages. The hypergiant UY Scuti, for instance, appears to be unusually massive for its age and location in the galaxy. It may have formed through the merger of two already massive stars, explaining its extreme properties. Binary interactions can also affect how a massive star dies. A close companion can strip away a star's outer layers, leaving behind a smaller, hotter core that will experience a different type of supernova. Alternatively, the companion might be engulfed during the primary star's expansion, leading to a common envelope phase and possibly a merger. The diversity of massive stellar evolution reminds us that nature rarely follows simple, linear paths. Each star's journey is unique, shaped by its initial conditions and environment. The hypergiants we observe represent just one possible outcome of massive stellar evolution, albeit one of the most spectacular. As we look deeper into space and further back in time, we may discover even more extreme stars in the early universe. The first generation of stars, formed from pristine hydrogen and helium before the universe was enriched with heavier elements, may have included true monsters with masses hundreds of times that of our Sun. These population 3 stars, as astronomers call them, have never been directly observed because they all died billions of years ago. But their influence shaped the early universe, creating the first heavy elements and seeding the cosmos with the materials needed for later generations of stars and planets. The study of massive stars thus connects us to the entire history of the universe, from its earliest epochs to the present day. By understanding how these stellar titans live and die, we gain insight into the processes that created the conditions for our own existence. In the next chapter, we'll zoom in on the truly mind-boggling scale of the largest known stars, attempting to comprehend just how enormous these cosmic leviathans really are. To truly comprehend the scale of the universe's largest stars, we need reference points. Our everyday experience on Earth simply doesn't prepare us for the reality of these cosmic titans. So let's begin our exploration of stellar scale by starting with something familiar, our own Sun, and then gradually work our way up to the true monsters of the stellar world. Our Sun, the star at the center of our solar system, is itself an object of tremendous size. With a diameter of about 1.4 million kilometers, it would take approximately 109 Earths lined up side by side to span the Sun's width. Put another way, you could fit about 1.3 million Earths inside the volume of the Sun. Light, traveling at 300,000 kilometers per second, takes about 4.5 seconds to cross from one side of the Sun to the other. If you could somehow fly around the Sun in a commercial airliner traveling at 900 kilometers per hour, the journey would take you about 65 days of continuous flight. These comparisons already stretch our imagination, but the Sun is merely average in the cosmic scheme. It's a G-type main sequence star, unremarkable in size compared to the giants that populate our galaxy. Moving up the stellar size scale, we encounter stars like Sirius A, the brightest star in our night sky. Sirius A is an A-type main sequence star with a diameter about 1.7 times that of our Sun. This modest increase in size comes with a substantial increase in brightness, as Sirius A shines with the light of about 26 suns. Continuing upward, we reach stars like Pollux, a K-type giant star in the constellation Gemini. With a diameter about 9 times that of our Sun, Pollux represents the first significant step up in our size exploration. Light takes about 40 seconds to cross from one side of Pollux to the other. Next come the standard red giants, stars similar in mass to our Sun but in a more advanced evolutionary stage. Arcturus, the brightest star in the northern celestial hemisphere, is a red giant with a diameter about 25 times that of our Sun. If placed at the center of our solar system, Arcturus would extend almost to Mercury's orbit, engulfing the innermost planet. But even Arcturus is dwarfed by the larger red giants. Aldebaran, the eye of the bull in the constellation Taurus, has a diameter about 44 times that of our Sun. Light takes over 3 minutes to travel from one side of Aldebaran to the other. Now we begin to enter the realm of the truly enormous. Rigel, a blue supergiant in the constellation Orion, has a diameter about 78 times that of our Sun. Despite being much hotter and more luminous than Aldebaran, Rigel is actually smaller in physical size, demonstrating that stellar size doesn't always correlate directly with brightness. Our next stop is Antares, a red supergiant in the constellation Scorpius, whose name literally means rival of Mars due to its reddish appearance. Antares has a diameter about 883 times that of our Sun. If placed at the center of our solar system, Antares would engulf the orbits of Mercury, Venus, Earth, and Mars, extending nearly to Jupiter. Light takes more than an hour to travel from one side of Antares to the other. The volume of Antares could contain approximately 685 million suns. The surface gravity of this stellar giant is so weak that if you could somehow stand on it, which of course would be impossible due to its gaseous nature and enormous heat, you would experience only about 1,000th of Earth's gravity. At this scale, we're already dealing with stars of almost incomprehensible size. But we're just getting started on our journey to the largest known stars in the universe. Next comes Betelgeuse, the famous red supergiant that forms the shoulder of Orion. Betelgeuse has been extensively studied due to its brightness and proximity, but measuring its exact size has proven challenging. Current estimates place its diameter at about 887 times that of our Sun, making it slightly larger than Antares. Betelgeuse is notable not just for its size, but for its variability. The star pulsates irregularly, changing in size and brightness over periods of months and years. In late 2019 and early 2020, Betelgeuse experienced an unusually deep dimming that was visible even to the naked eye, causing speculation about an imminent supernova. Further observations revealed that the dimming was likely caused by a combination of the star's normal pulsation cycle and a large dust cloud ejected from its surface. This variability reminds us that the sizes we quote for these stellar giants are not fixed values, but averages that can fluctuate significantly over time. The boundary between star and surrounding space is also somewhat arbitrary for these objects, as their outer layers become increasingly tenuous with distance from the core. Moving further up the size scale, we encounter Vivi Cephei, a red supergiant in the constellation Cepheus. Vivi Cephei has a diameter estimated at between 1,100 and 1,600 times that of our Sun. The wide range in these estimates reflects the difficulty in precisely measuring such enormous and distant objects. Vivi Cephei is part of a binary system, with a smaller, hotter companion star orbiting around it. When the companion passes behind Vivi Cephei, it creates an eclipse that lasts for over a year, allowing astronomers to study the structure of the supergiant's extended atmosphere. Next, in our cosmic size comparison comes V354 Cephei, a red hypergiant with a diameter approximately 1,520 times that of our Sun. If placed at the center of our solar system, V354 Cephei would extend beyond the orbit of Jupiter. At this scale, we're dealing with a single star that's larger than the entire inner solar system. The volume of V354 Cephei could contain about 3.5 billion suns. Light takes more than 2.5 hours to travel from one side of this star to the other. Now we approach the current record holders for the largest known stars in the universe. These measurements are still subject to revision as observational techniques improve, but they represent our best current understanding of the upper limits of stellar size. VY Canis Majoris, a red hypergiant in the constellation Canis Major, was once thought to be the largest known star. More recent measurements have revised its size downwards somewhat, but it remains one of the largest stars known, with a diameter approximately 1,420 times that of our Sun. VY Canis Majoris is notable not just for its enormous size, but for the complex nebula surrounding it. This nebula, created by multiple episodes of mass loss, extends much further than the star itself and contains enough material to make several suns. The star is losing mass at a rate of about 30 times the mass of Earth each year, creating the spectacular structures we observe. The current contender for the title of largest known star is UY Scuti, a red supergiant or hypergiant in the constellation Scutum. Discovered in 1860 by German astronomers at the Bonn Observatory, UY Scuti remained relatively obscure until modern measurements revealed its extraordinary size. In 2013, astronomers using the Very Large Telescope Interferometer in Chile measured UY Scuti's angular diameter and combined this with distance estimates to calculate its physical size. They found that UY Scuti has a diameter approximately 1,708 times that of our Sun, with a margin of error of about 192 solar diameters. If placed at the center of our solar system, UY Scuti would engulf the orbit of Jupiter. Its surface would extend to about 7.9 astronomical units from the center, compared to Jupiter's average orbital distance of 5.2 astronomical units. Light takes about 7 hours to travel from one side of UY Scuti to the other. The volume of UY Scuti could contain approximately 5 trillion suns. Its mass, however, is estimated to be only about 7 to 10 times that of our Sun, meaning its average density is incredibly low, less than 1/1,000,000th the density of Earth's atmosphere at sea level. The outer layers of UY Scuti are so tenuous that they would be considered a high vacuum by terrestrial standards. But even UY Scuti may be overshadowed by one more stellar giant. Stephenson 2-18, a red supergiant in the Stephenson 2-star cluster, might be even larger. Some estimates place its diameter at up to 2,150 times that of our Sun, though this measurement has greater uncertainty than that of UY Scuti. If these measurements are accurate, Stephenson 2-18 would extend beyond the orbit of Saturn if placed at the center of our solar system. Its volume could contain over 8 trillion suns. Light would take about 9 hours to travel from one side of this cosmic leviathan to the other. It's worth noting that the sizes of these extreme stars are not precisely known and remain subjects of ongoing research. Different measurement techniques and assumptions about the star's distances can lead to significantly different size estimates. The figures quoted here represent current best estimates, but should be understood as having substantial margins of error. What's not in doubt, however, is the truly staggering scale of these objects. They represent the upper limit of what's physically possible for a single star. Their existence pushes against the theoretical boundaries of stellar structure, creating objects so large that they exist in a state of constant struggle against their own gravity. To appreciate the true enormity of these stars, let's consider some additional comparisons and thought experiments. If our Sun were the size of a golf ball, about 4.3 centimeters in diameter, the Earth would be a tiny speck, just 0.4 millimeters across, located about 4.6 meters from the golf ball. On this scale, UY Scuti would be a sphere 73 meters in diameter, roughly the height of a 20-story building. Or consider this: if you could travel at the speed of light, you could circle the Earth about 7.5 times in 1 second. You could travel from the Earth to the Moon in about 1.3 seconds. But to travel from one side of UY Scuti to the other would take you about 7 hours, roughly the time it takes to fly from New York to London. Another way to visualize the scale is to consider the volume of these stars. The volume of a sphere increases with the cube of its radius, so even a modest increase in diameter results in a dramatic increase in volume. UY Scuti has a diameter about 1,700 times that of our Sun, but its volume is about 5 trillion times greater. This means that if both stars were hollow, you could fit 5 trillion suns inside UY Scuti with room to spare. That's almost 700,000 suns for every human being alive on Earth today. The surface area of these stellar giants is similarly immense. UY Scuti has a surface area about 3 million times that of our Sun, or about 800 billion times the surface area of Earth. If UY Scuti's surface were flattened out, it would cover an area equivalent to 163 billion Earths laid side by side. These comparisons help us grasp the numerical scale of these objects, but they still don't capture the full reality of what it would mean to encounter such a star in space. Let's engage in a thought experiment to bring this home. Imagine you're in a spacecraft approaching UY Scuti from a great distance. Initially, it appears as an intensely bright star, already outshining all others. As you draw closer, it begins to resolve into a visible disk, growing larger in your viewport. By the time you're as far from UY Scuti as Earth is from the Sun, the star would fill nearly 1/3 of your entire field of view. Its apparent size would be over 300 times that of the Sun as seen from Earth. At this distance, the heat and radiation would be intense, but your spacecraft's shielding might still protect you. Move closer, however, and the situation quickly becomes more extreme. By the time you reach the orbit of Mercury, UY Scuti would fill nearly your entire field of view, a vast wall of glowing plasma extending in all directions. The radiation at this distance would be immediately fatal, and no known material could shield against it for long. Your spacecraft would begin to melt and vaporize from the intense heat. But even if you could somehow survive, the view would be unlike anything humans have ever experienced, a nearly flat horizon of incandescent gas stretching to the limits of vision. If you could somehow penetrate to the star's outer atmosphere, you would find yourself in a realm of superheated gas so diffuse that it would be considered a vacuum on Earth. Yet this material would still be hot enough to vaporize any known substance. As you descended deeper, the gas would gradually become denser, transitioning almost imperceptibly from the vacuum of space to the outer atmosphere of the star. This gradual boundary is part of what makes measuring the exact size of hypergiants so challenging. Unlike the Sun, which has a relatively well-defined photosphere, the outer layers of a hypergiant blend smoothly into the surrounding space. The point at which we consider the star to end becomes somewhat arbitrary, usually defined as the radius at which the gas becomes opaque to a certain wavelength of light. The enormity of hypergiants also impacts their other physical properties in extreme ways. Their surface gravity, for instance, is incredibly weak despite their enormous mass. UY Scuti may have about 7 to 10 times the mass of our Sun, but this mass is spread over a volume trillions of times larger. As a result, the gravitational acceleration at its surface is estimated to be about 1/10,000th that of Earth. This weak surface gravity has important consequences for the star's structure and evolution. It means that material can easily escape from the surface, blown away by the intense radiation pressure from within. UY Scuti is losing mass at a prodigious rate, shedding enough material each year to make several Earths. The tenuous nature of a hypergiant's outer layers also affects its appearance. Unlike smaller stars, which appear as well-defined disks when viewed through powerful telescopes, hypergiants often have indistinct boundaries and may be surrounded by complex nebulae of ejected material. This makes them visually spectacular, but adds to the difficulty of determining where the star ends and the surrounding nebula begins. Another consequence of their enormous size is that hypergiants are inherently unstable. They exist at the upper limits of what's physically possible for a star, constantly battling against their own gravity and radiation pressure. This instability manifests in various ways, from pulsations that cause the star to expand and contract over months or years, to violent eruptions that eject huge amounts of material into space. The physical mechanisms that create and maintain stars of such enormous size are still not fully understood. They represent extreme cases in stellar evolution, pushing against the theoretical boundaries of what stars can be. Their study continues to challenge and refine our understanding of stellar physics. One thing is clear, however: these stars cannot maintain their enormous size indefinitely. The same instability that makes them so fascinating also ensures that their current state is temporary. Eventually, they will either shed enough mass to become smaller, more stable stars, or they will exhaust their nuclear fuel and collapse, likely exploding as supernovae. The lifespans of hypergiants are dramatically shorter than those of smaller stars. While our Sun will shine steadily for about 10 billion years, UY Scuti may remain in its current hypergiant phase for only a few tens of thousands of years. This brief cosmic moment is another reason these stars are so rare. We're lucky to catch them during the short period when they reach their maximum size. Despite their rarity and distant locations, hypergiants have fascinated astronomers since their discovery. They represent the extreme end of stellar evolution, showcasing the full range of what's possible in the lives of stars. They also play crucial roles in galactic evolution, enriching their surroundings with heavy elements and potentially triggering new rounds of star formation when they explode. As our observational capabilities improve, we may discover even larger stars lurking in distant corners of the galaxy or in nearby galaxies. But there are theoretical reasons to believe that stars much larger than those we've already found cannot exist. Physical constraints on stellar structure, particularly the Eddington limit that balances gravity against radiation pressure, suggest that stars with diameters beyond about 2,000 to 2,500 times that of our Sun would be too unstable to form or maintain themselves. This means that stars like UY Scuti and Stephenson 2-18 may represent the upper limit of what's possible in nature. They stand as cosmic extremes, showcasing the maximum size a single object can achieve through the normal processes of stellar evolution. Before we leave our exploration of stellar scale, it's worth reflecting on one more aspect of these cosmic giants: their position in the larger hierarchy of cosmic structures. As incomprehensibly large as hypergiants are compared to human scale, they are themselves tiny compared to larger cosmic structures. A hypergiant like UY Scuti extends to perhaps 8 astronomical units in radius. But the Oort cloud, the spherical shell of icy objects that marks the outer boundary of our solar system, extends to about 100,000 astronomical units. Our entire Milky Way galaxy spans about 100,000 light-years, or about 600 million astronomical units, and the observable universe extends about 46 billion light-years in all directions. So while hypergiants represent the largest single objects of their kind, they are still infinitesimal compared to the full scale of the cosmos. A hypergiant in our galaxy would be like a single cell in a human body, important and complex in its own right, but a tiny component of a much larger structure. This nested hierarchy of scale, from subatomic particles to hypergiants to galaxy clusters to the observable universe, helps us appreciate both the enormity of these stellar giants and their place in the cosmic order. They are among the largest single objects in existence, yet still mere specks in the unfathomable vastness of space. In the next chapter, we'll delve into another aspect of these stellar monsters, the incredible energy they produce, and the fundamental physics that powers their luminous existence. But before we move on, let's take a moment to consider what it would be like to view these stellar behemoths from different perspectives. Imagine you're an astronomer living on a planet orbiting a star at a safe distance from UY Scuti, perhaps 20 astronomical units away, similar to Uranus's distance from our Sun. From this vantage point, UY Scuti would dominate your sky in a way that's difficult for us Earthlings to comprehend. It would appear not as a disk like our Sun, but as an enormous glowing wall stretching across a significant portion of your sky. Its apparent diameter would be over 100 times that of our Sun, as seen from Earth. The light from UY Scuti would illuminate your world with a deep red glow, significantly different from the yellowish-white light of our Sun. Despite being much cooler than our Sun, with a surface temperature of around 3,400 Kelvin compared to our Sun's 5,800 Kelvin, UY Scuti would still provide substantial heat due to its enormous size. At certain times in its pulsation cycle, UY Scuti might brighten dramatically, causing noticeable changes in the illumination of your world. These pulsations, which can cause the star to vary in brightness by a factor of 2 or more, would be a regular feature of your sky, a cosmic heartbeat marking the passage of time. Now imagine you're an intrepid explorer in a specially shielded spacecraft, approaching the surface of UY Scuti as closely as physically possible, without being destroyed by its heat and radiation. As you draw near, the star's horizon would flatten out due to its enormous size, creating the illusion that you're approaching a wall rather than a sphere. The outer atmosphere would be remarkably tenuous, with a density less than the best vacuum we can create on Earth. Yet this incredibly diffuse gas would still be hot enough to vaporize most materials. Your spacecraft would need extraordinary shielding just to approach the star's outer layers. If you could somehow take a sample of this outer atmosphere and bring it back to Earth, it would behave more like an extremely hot, diffuse plasma than what we typically think of as gas. Its density might be just a few hundred or thousand atoms per cubic centimeter, compared to about 10 to the 25th atoms per cubic centimeter in the air we breathe. As you descended deeper into the star's atmosphere, the gas would gradually become denser, but even thousands of kilometers below what we define as the surface, it would still be less dense than Earth's atmosphere. This gives you a sense of just how diffuse these enormous stars are. The view from inside the outer atmosphere would be unlike anything experienced on Earth. Looking outward, you would see the blackness of space. Looking inward, you would see an all-encompassing glow, growing brighter as it extended toward the center of the star. There would be no distinct boundary, no clear horizon, just a gradual transition from the vacuum of space to the sparse outer atmosphere to the denser, hotter interior. If we could somehow place a solid object like a spacecraft or a planet inside the outer layers of UY Scuti, it might not even notice any significant aerodynamic drag despite moving through the star's material. The gas is simply too tenuous to create much resistance. However, the intense heat would quickly vaporize any known material. This brings us to another interesting aspect of Hypergean scale, the concept of optical depth. Astronomers define the photosphere of a star, what we typically consider its visible surface, as the layer where the optical depth equals 2/3. This is the point at which light can travel, on average, a certain distance before being absorbed or scattered. For a hypergeant like UY Scuti, this transition happens so gradually across such an enormous volume that the concept of a surface becomes almost meaningless. It's more accurate to think of the star as having layers of increasing density and temperature rather than a distinct boundary. This gradual transition has important implications for how we measure the size of these stars. Different observational techniques, operating at different wavelengths, may place the star's boundary at different points in this gradient. This is one reason why size estimates for hypergeants can vary significantly depending on the method used. The challenge of defining exactly where a hypergeant ends becomes even more complicated when we consider the surrounding nebula. Many hypergiants are embedded in complex clouds of material they've ejected during previous mass loss events. This material, while no longer part of the star itself, is intimately connected to it, shaped by its stellar winds and illuminated by its light. For a star like VY Canis Majoris, the surrounding nebula extends to hundreds of times the radius of the star itself. This nebula contains detailed structures, arcs, knots, and filaments that record the history of the star's mass loss over thousands of years. From a distance, it can be difficult to distinguish where the star ends and the nebula begins. Let's extend our exploration of stellar scale by considering some additional hypergiants and comparing their sizes to familiar cosmic structures. NML Cygni is another red hypergiant, located in the constellation Cygnus about 5,200 light-years from Earth. Recent measurements suggest its diameter is approximately 1,650 times that of our Sun, making it one of the largest known stars. If placed at the center of our solar system, NML Cygni would extend beyond the orbit of Jupiter. The star is losing mass rapidly, creating a circumstellar envelope that extends even further, to about 15 astronomical units, almost reaching the orbit of Uranus. Another noteworthy giant is KY Cygni, a red supergiant in the constellation Cygnus, with a diameter estimated at about 1,420 times that of our Sun. Like other stars of its class, KY Cygni has a complex outer atmosphere and is likely surrounded by ejected material from past mass loss events. One particularly interesting case is the star WOHG 64 in the Large Magellanic Cloud, a satellite galaxy of our Milky Way. This red supergiant has a diameter approximately 1,540 times that of our Sun, but what makes it remarkable is that we're observing it in another galaxy, about 160,000 light-years away. The fact that we can measure the size of individual stars in other galaxies is a testament to the power of modern astronomical techniques. It also reinforces how truly enormous these hypergiants are, visible and measurable even across intergalactic distances. To put the scale of these stars in yet another perspective, let's compare them to other large structures in our solar system. The diameter of UY Scuti, about 2.4 billion kilometers, is approximately 16 times the diameter of Jupiter's orbit around the Sun. It's about 5 times the diameter of Saturn's orbit and twice the diameter of Uranus's orbit. If we were to replace our Sun with UY Scuti, the Earth and all the inner planets would be deep inside the star, as would Jupiter and Saturn. Only Uranus and Neptune would orbit outside the star's surface, and even then, not by much. The habitable zone, where liquid water can exist on a planet's surface, would be pushed out to hundreds or thousands of astronomical units from the star. This brings up an interesting question. Could planets exist around such enormous stars? The answer is complicated. During their main sequence phase, before expanding to become hypergiants, these stars were extremely massive and luminous, but much smaller in diameter. They could have had planetary systems during this phase, although the intense radiation would have made conditions hostile for life as we know it. As the star expanded to become a hypergiant, it would engulf any inner planets. Outer planets might survive, but would be subjected to intense stellar winds and increased luminosity. Additionally, hypergiants lose mass at such a high rate that the orbits of any surviving planets would change over time, moving outward as the star's mass decreases. Another factor to consider is the short lifespan of hypergiants. These stars remain in their largest state for only tens or hundreds of thousands of years before either shrinking due to mass loss or exploding as supernovae. This is a cosmic eye blink, far too short for complex life to evolve. Any civilization that happened to find itself in a system with a hypergiant star would have very little time to admire the view before facing extinction. Let's take a moment to consider the historical context of our understanding of stellar size. For most of human history, stars were considered tiny points of light, their true nature and scale completely unknown. Even after the Copernican revolution established that the Sun is a star, its true size and the existence of stars much larger than it remained undiscovered until relatively recent times. The first systematic measurements of stellar sizes began in the early 20th century with the development of interferometry, a technique that combines light from multiple telescopes to achieve resolution fine enough to measure the disks of nearby stars. The first such measurement was performed on Betelgeuse in 1920 by Albert Michelson and Francis Pease using the Mount Wilson Observatory. This groundbreaking work revealed for the first time that some stars are significantly larger than our Sun. Betelgeuse was found to have a diameter hundreds of times that of the Sun, a revelation that transformed our understanding of stellar diversity. As observational techniques improved throughout the 20th century, astronomers discovered ever larger stars. VY Canis Majoris was recognized as an extraordinary object by the 1970s, and the current record holders like UY Scuti and Stevenson, 2-18, were measured accurately only in the past decade or two. This progressive discovery of larger and larger stars mirrors the general expansion of our cosmic horizons over the past century. From a time when the Milky Way was thought to be the entire universe, we now recognize it as just one of hundreds of billions of galaxies in the observable universe. Similarly, from a time when our Sun was thought to be a typical star, we now understand the tremendous range of stellar sizes, from tiny red dwarfs to the hypergiants we've been discussing. The discovery of these stellar giants has implications that go beyond mere record-keeping. It helps us understand the physical limits of stellar structure, the life cycle of massive stars, and the role these cosmic monsters play in chemical enrichment of the universe. For instance, the existence of stars approaching 2,000 times the diameter of our Sun challenges theoretical models of stellar structure. At such enormous sizes, the outer layers of the star are only tenuously bound by gravity, leading to extreme instability and mass loss. Understanding how such stars can exist, even temporarily, requires sophisticated modeling of stellar physics. The scale of hypergiants also affects their observable properties in ways that astronomers are still working to fully understand. Their enormous size combined with relatively low surface temperatures makes them exceptionally luminous in infrared wavelengths. This has implications for how we interpret observations of distant galaxies, where unresolved hypergiants may contribute significantly to the overall infrared emission. As our observational capabilities continue to improve, we may discover even more extreme stars. The James Webb Space Telescope, with its exceptional infrared sensitivity, is particularly well suited to studying cool, red objects like hypergiants. It may reveal previously unknown examples in distant parts of our galaxy or in nearby galaxies. However, there are theoretical reasons to believe that we've already discovered stars close to the maximum possible size. The physical constraints on stellar structure, particularly the balance between gravity and radiation pressure, suggest that stars much larger than UY Scuti or Stevenson 2-18 would be too unstable to exist for any significant period. This doesn't mean we won't find slightly larger examples, perhaps stars up to 2,500 or 3,000 times the diameter of our Sun. But stars dramatically larger than this would likely tear themselves apart almost immediately due to their own radiation pressure and weak surface gravity. The largest stars thus represent a kind of cosmic limit, showcasing the maximum size a single, coherent object can attain under the laws of physics as we understand them. They stand as monuments to the extreme conditions possible in our universe, reminders of both the vastness of cosmic scales and the physical constraints that even the largest objects must obey. In the next chapter, we'll shift our focus from the sheer size of these stellar giants to the incredible energy they produce, exploring the nuclear furnaces at their cores and the staggering amounts of radiation they pour into space. The sheer size of hypergiants is only one aspect of their extraordinary nature. Equally impressive is the staggering amount of energy these stellar titans produce and radiate into space. In this chapter, we'll explore the enormous power output of these cosmic monsters, the nuclear processes that fuel them, and the profound impact their energy has on their surroundings. To begin our exploration of stellar energy, let's start with a familiar reference point, our Sun. Every second, the Sun converts about 600 million tons of hydrogen into helium through nuclear fusion. This reaction releases energy equivalent to the explosion of 92 billion 1 megaton hydrogen bombs every single second. The total power output of the Sun is about 384 yottawatts. A yottawatt is 1 trillion watts, or 10 raised to the power of 24 watts. This is more energy than human civilization has produced throughout its entire history. Yet in the grand cosmic scheme, our Sun is a modest energy producer. The most luminous stars outshine it by factors of millions. Stars produce energy through nuclear fusion, the process by which lighter elements combine to form heavier ones, releasing energy in the process. In main sequence stars like our Sun, the primary reaction is the fusion of hydrogen into helium, specifically through what's called the proton-proton chain, or, in more massive stars, the CNO cycle. These reactions occur in the star's core, where temperatures reach millions of degrees Celsius and pressures are billions of times greater than Earth's atmospheric pressure. Under these extreme conditions, atomic nuclei can overcome their natural electromagnetic repulsion and fuse together. The energy released by fusion creates an outward pressure that counteracts the inward pull of gravity, maintaining the star in a state of hydrostatic equilibrium. This balance between gravity and pressure is what allows stars to shine steadily for millions or billions of years. As we move up the stellar mass scale, the core temperature and pressure increase, allowing fusion to proceed more rapidly. A star with 10 times the mass of our Sun might be 1,000 times more luminous. This relationship between mass and luminosity becomes even more extreme for the most massive stars. The hypergiants we've been discussing began their lives as extremely massive main sequence stars, perhaps 40 to 100 times the mass of our Sun. At this mass, their core temperatures would have been tens of millions of degrees Celsius, allowing for incredibly rapid rates of nuclear fusion. A main sequence star with 60 times the mass of our Sun might shine with the brightness of nearly 1 million suns. This explains why massive stars live such short lives. They burn through their nuclear fuel at a prodigious rate. As these massive stars evolve into supergiants and hypergiants, their energy production becomes even more complex. The core, having exhausted its hydrogen, contracts and heats up, initiating helium fusion. Meanwhile, hydrogen fusion continues in a shell around the core. This layered fusion structure is far more efficient at converting mass to energy than the simpler core fusion of a main sequence star. As a result, the luminosity of the star increases dramatically, often reaching millions of times that of our Sun. Let's consider some specific examples. UY Scuti, one of the largest known stars, has a luminosity estimated at around 340,000 times that of our Sun. Despite having a mass only about 7 to 10 times solar, it produces energy at a rate comparable to thousands of stars like our Sun combined. An even more extreme case is the star R136A1 in the Tarantula Nebula. While not among the largest stars by diameter, it's one of the most massive known, with perhaps 215 times the mass of our Sun. Its luminosity is estimated at about 8.7 million times that of our Sun, making it one of the most powerful stellar energy sources known. The hypergiant Eta Carinae, famous for its 19th century eruption, radiates energy at a rate about 5 million times that of our Sun. During its great eruption in the 1840s, it briefly reached a luminosity of around 50 million times solar, making it one of the most energetic stellar events ever observed that wasn't a supernova. These numbers are so large that they become difficult to comprehend. Let's try to put them in context. If our Sun were replaced by UY Scuti, Earth would receive about 340,000 times more solar energy. The average temperature on Earth would soar to thousands of degrees, enough to melt rock and vaporize the oceans. Even at Neptune's distance, 30 times farther from the Sun than Earth, the heat would be more than 10 times what Earth currently receives. The radiation from a hypergiant would sterilize any planet within thousands of astronomical units. Their habitable zones, the regions where liquid water could exist on a planet's surface, would be pushed out to tens of thousands of astronomical units, far beyond the gravitational influence of the star itself. The energy output of hypergiants is so immense that it creates physical effects not seen in smaller stars. One of the most significant is radiation pressure, the actual physical push that electromagnetic radiation exerts on matter. In stars like our Sun, radiation pressure plays a minor role in the overall structure. Gravity is the dominant force, with gas pressure providing the necessary outward support. But in hypergiants, radiation pressure becomes a major factor, sometimes exceeding gas pressure in supporting the outer layers against gravity. This shift to radiation-dominated support has profound implications for stellar stability. Radiation pressure responds differently to compression than gas pressure does, creating conditions where small perturbations can grow into large-scale instabilities. These radiation-driven instabilities manifest in various ways, from pulsations that cause the star to expand and contract over months or years, to violent eruptions that eject massive shells of material. The Great Eruption of Eta Carinae, which ejected more than 10 solar masses of material, was likely triggered by radiation pressure exceeding the star's gravitational binding force in its outer layers. Another consequence of the enormous energy production in hypergiants is their powerful stellar winds. All stars lose some mass through stellar winds, streams of charged particles flowing outward from their surfaces. Our Sun loses about 1.5 million tons of material per second this way, an amount that sounds large but represents only a tiny fraction of its total mass over its lifetime. Hypergiants, by contrast, can lose mass at rates billions of times greater. UY Scuti might shed more than 1 Earth mass of material every year. Over millennia, this adds up to substantial mass loss, with some hypergiants ejecting tens of solar masses during their lifetimes. These powerful stellar winds are driven primarily by radiation pressure. Photons streaming outward from the star's interior collide with atoms in the outer atmosphere, transferring momentum and accelerating them away from the star. The enormous luminosity of hypergiants means there are many more photons available to drive this process, resulting in much stronger winds. The material carried away by these winds forms complex nebulae around many hypergiants. These nebulae can extend for light years, containing enough material to form multiple new stars. They're often structured into shells, arcs, or bipolar outflows, shaped by the star's rotation, magnetic fields, and episodic mass loss events. For instance, the nebula surrounding VY Canis Majoris extends more than 10 light days from the star and contains enough material to make several suns. Its complex structure records the history of the star's mass loss over thousands of years, with different features corresponding to distinct eruption events. The energy output of hypergiants also manifests in their surface temperatures. Despite their classification as cool stars, with surface temperatures typically around 3,000 to 4,000 Kelvin, the total amount of energy they radiate is enormous due to their vast surface areas. This leads to an interesting paradox. Hypergiants like UY Scuti appear red or orange when observed visually, indicating relatively cool surface temperatures. Yet they pour out energy at a rate millions of times greater than the Sun. The apparent contradiction is resolved when we consider their enormous size. A cool but incredibly vast surface can still radiate tremendous amounts of energy. The spectral characteristics of hypergiants reflect this unique combination of high energy output and relatively cool surfaces. They emit strongly in infrared wavelengths, with spectra showing absorption lines from molecules that can only form at lower temperatures, such as titanium oxide and water vapor. These molecular features would be destroyed by the heat in hotter stars. At the same time, their spectra show signs of extreme conditions not found in ordinary stars. Broad emission lines indicate high-velocity gas flows. Unusual chemical signatures reveal elements dredged up from the stellar interior by convection or produced through enhanced nuclear processing. And variable features in the spectrum document the pulsations and eruptions that characterize these unstable stellar giants. The internal energy transport in hypergiants is also distinctive. In stars like our Sun, energy moves outward from the core through a combination of radiation and convection. Photons carry energy through the radiative zone, while bulk movements of plasma transport heat through the convective zone. In hypergiants, the enormous energy flux and extended structure create a more complex situation. Multiple convective zones can form, separated by radiative regions. Convective cells can be enormous, with individual upwellings and downflows spanning distances greater than the diameter of our Sun. These giant convection cells create observable effects at the star's surface. Doppler imaging of Betelgeuse, for instance, has revealed enormous bright and dark patches corresponding to hotter upwelling and cooler downflowing material. These features are like sunspots on our Sun but scaled up enormously, with individual cells larger than the orbit of Mars. The enormous energy output of hypergiants also challenges our understanding of stellar evolution. According to the standard mass-luminosity relationship for main sequence stars, a star with 10 times the mass of our Sun should be about 10,000 times more luminous. But hypergiants with similar masses can be hundreds of thousands of times more luminous than the Sun. This discrepancy arises because hypergiants are not main sequence stars. They've evolved into a very different state, with multiple fusion shells and drastically altered internal structures. Their luminosity comes not just from their mass, but from their evolutionary state, particularly the compressed, hot helium or carbon-burning core surrounded by a hydrogen-burning shell. The energy production in hypergiants is so intense that they literally live on the edge of stability. They approach what astronomers call the Eddington limit, the theoretical maximum luminosity a star can have before radiation pressure overcomes gravity and begins to blow the star apart. Stars that exceed the Eddington limit cannot maintain a stable structure. Their outer layers are accelerated outward by radiation pressure, resulting in extreme mass loss or even explosive events. Some astronomers believe that stars like Eta Carinae periodically exceed the Eddington limit in their outer layers, triggering the massive eruptions observed in their histories. This brings us to an important realization. The enormous size of hypergiants is directly connected to their enormous energy output. As these stars evolve and their luminosity increases, radiation pressure pushes their outer layers outward, causing them to expand to their gigantic dimensions. Without their tremendous energy production, they could never maintain their enormous volumes against the pull of gravity. Yet this same energy that allows hypergiants to exist also ensures their structures are temporary. The powerful radiation drives mass loss that will eventually reduce the star to a more stable configuration or trigger a supernova explosion. The hypergiants we observe are cosmic fireworks, spectacular but brief flashes in the grand history of stellar evolution. The effects of a hypergiant's energy extend well beyond the star itself. These stellar monsters have profound impacts on their surroundings, shaping the interstellar medium and potentially triggering new rounds of star formation. The intense ultraviolet radiation from a hypergiant can ionize gas clouds up to dozens of light-years away, creating what astronomers call H2 regions, bubbles of hot, glowing plasma. These regions are visible across vast cosmic distances and serve as markers of massive star formation in other galaxies. The powerful stellar winds from hypergiants sweep up interstellar material, creating shells or bubbles of compressed gas. These shells can become unstable and collapse under their own gravity, forming new stars. This process of triggered star formation is an important mechanism for propagating starbirth through giant molecular clouds. When multiple massive stars form in proximity, their combined winds and radiation can create even larger structures, such as superbubbles spanning hundreds of light-years. These features shape the large-scale structure of galaxies and influence where future generations of stars will form. The chemical impact of hypergiants is equally significant. Through nuclear fusion in their cores and the subsequent dispersal of material through stellar winds and eventual supernovae, these stars are primary sources of heavy elements in the universe. Elements like carbon, oxygen, silicon, and iron are forged in the interiors of massive stars and then distributed through space when the stars shed mass or explode. Without the brief, intense lives of stellar giants, the universe would be composed almost entirely of hydrogen and helium, lacking the chemical diversity needed for planets and life. Perhaps the most spectacular demonstration of a hypergiant's energy comes at the end of its life. When such a star finally exhausts all possible nuclear fuels, its core collapses, triggering a supernova explosion. In a matter of seconds, the star releases more energy than it produced in its entire multi-million-year lifetime. A typical core collapse supernova releases around 10 to the 44 joules of energy, equivalent to the energy the Sun will produce over 10 billion years. For a few weeks, a single dying star can outshine an entire galaxy containing hundreds of billions of stars. This brings us to a humbling perspective on cosmic energy scales. As enormous as the ongoing energy production of hypergiants is, it pales in comparison to the cataclysmic events that mark the deaths of the most massive stars. And even these supernovae are dwarfed by more extreme cosmic phenomena, like gamma-ray bursts or quasars, powered by supermassive black holes. The universe operates on energy scales that defy human comprehension, from the microscopic fusion of atomic nuclei, to the star-spanning convection cells of hypergiants, to the galaxy-shaping effects of supernovae. Cosmic processes involve amounts of energy that make all human endeavors seem insignificant by comparison. Yet through science and observation, we've managed to understand these processes, to measure the luminosity of stars millions of light years away, and to reconstruct the nuclear reactions occurring in their cores. This understanding represents one of humanity's greatest intellectual achievements, allowing us to comprehend phenomena that operate on scales far beyond direct human experience. As we contemplate the enormous energy of stellar giants, we're reminded that our Sun, impressive as it is, represents just one point in a vast spectrum of stellar power. From the faintest red dwarfs, with less than 1,000th the luminosity of our Sun, to hypergiants shining with the light of millions of suns, stars showcase the full range of what's possible when gravity compresses matter to the point where nuclear fusion begins. And perhaps most remarkably, all of this stellar energy, from the smallest to the largest stars, ultimately derives from the same fundamental force: the strong nuclear interaction that binds protons and neutrons together in atomic nuclei. The same physics that powers a red dwarf's feeble glow also drives the tremendous energy output of the largest hypergiants. Only the scale differs, not the basic principles. In our next chapter, we'll explore what happens when these enormous reserves of stellar energy are finally exhausted, examining the spectacular deaths of the largest stars in the universe and the exotic remnants they leave behind. All stars, even the greatest giants in the universe, eventually meet their end. But the deaths of hypergiants are unlike anything else in the cosmos, cataclysmic events of such power and violence that they momentarily outshine entire galaxies and seed the universe with the building blocks of future worlds. In this chapter, we'll explore the final days, hours, and seconds in the lives of the largest stars and the exotic remnants they leave behind. To understand the death of a hypergiant, we first need to understand why stars die at all. The answer lies in the fundamental balance between gravity and pressure that keeps a star stable. Throughout most of a star's life, the inward pull of gravity is precisely counterbalanced by the outward push of pressure generated by nuclear fusion in the core. As long as the star has fuel to burn, this equilibrium can be maintained. But no star has an infinite supply of fuel. Eventually, even the most massive stars exhaust the materials that can undergo energy-producing fusion reactions. When this happens, the balance shifts irreversibly toward gravity, and the star's structure begins to collapse. For stars like our Sun, this process is relatively gentle. When the Sun exhausts the hydrogen in its core about 5 billion years from now, it will expand into a red giant, then shed its outer layers to form a planetary nebula, leaving behind a white dwarf, a dense, Earth-sized stellar remnant that will slowly cool over trillions of years. But for the stellar monsters we've been discussing, death is far more violent. A hypergiant like UY Scuti follows a more complex evolutionary path, burning through a succession of different nuclear fuels at an accelerating pace. Let's follow the final stages in the life of a typical hypergiant to understand the processes that lead to its spectacular demise. We'll use a star with an initial mass of about 40 times that of our Sun as our example, though the details can vary significantly depending on the exact mass and composition of the star. After spending just a few million years on the main sequence, burning hydrogen in its core, our hypergiant exhausts this primary fuel. The core contracts and heats up until it reaches temperatures high enough to fuse helium into carbon and oxygen. Meanwhile, the outer layers expand dramatically, and the star becomes a red supergiant. The helium-burning phase lasts only about 500,000 years, a mere fraction of the star's already brief lifetime. When the core helium is depleted, the cycle of contraction, heating, and new fusion reactions continues, but on an increasingly compressed timeline. Carbon fusion begins at temperatures around 800 million degrees Celsius and lasts about 600 years. Neon fusion follows at 1.6 billion degrees, lasting about a year. Oxygen fusion requires temperatures around 2 billion degrees and runs its course in just 6 months. Finally, silicon fusion ignites at 3.3 billion degrees Celsius, burning through its fuel in a single day. This accelerating pace of nuclear burning creates an onion-like structure within the star. At the center lies an iron core, surrounded by shells of silicon, oxygen, neon, carbon, helium, and hydrogen, each undergoing fusion reactions at different rates. But when the core begins producing iron, the star reaches a critical juncture. iron represents the end of profitable fusion. Lighter elements release energy when fused into heavier elements, but fusing iron actually consumes energy rather than producing it. Once a substantial iron core forms, the star's fate is sealed. With no new energy source available, the iron core continues to grow as overlying layers fuse and add to it. When the core reaches about 1.4 times the mass of our Sun, something remarkable happens. The core has become so dense that electrons are forced into atomic nuclei, combining with protons to form neutrons in a process called electron capture. This suddenly reduces the electron degeneracy pressure that had been supporting the core against gravity. What follows happens with astonishing rapidity. The core collapses from about 7,000 kilometers across to just 40 kilometers in less than a second. This implosion occurs at speeds up to 23% of the speed of light, releasing gravitational potential energy equivalent to more than 100 times the energy the Sun will release over its entire 10 billion year lifetime. As the collapsing material hits the incompressible neutron core, it rebounds, creating a shockwave that begins to move outward. Simultaneously, an enormous flood of neutrinos, subatomic particles produced during electron capture, streams out from the core, carrying away about 99% of the collapse energy. Some of these neutrinos interact with the infalling material, depositing additional energy that helps drive the shockwave outward through the star. This combination of shock and neutrino heating tears through the star's layers at speeds of up to 10% the speed of light. When the shockwave reaches the star's surface, roughly 3 hours after core collapse begins, we see the first visible sign of the supernova, a sudden brightening as the star's outer layers are heated to millions of degrees. The star rapidly increases in brightness, reaching its peak luminosity within a few days. At its maximum, a typical Type II supernova, as these core collapse events are called, can shine with the light of several billion suns. For a period of days to weeks, a single dying star can outshine the entire galaxy containing it. The supernova's visible light comes from two main sources: the initial shock breakout that heats the star's outer layers, and the subsequent radioactive decay of unstable isotopes produced during the explosion. Elements like nickel-56 are created in abundance during the supernova and decay, first to cobalt-56 and then to stable iron-56, releasing gamma rays that are absorbed and re-emitted as visible light. This radioactive decay powers the supernova's light curve, the plot of its brightness over time. After reaching its peak, the supernova gradually fades over a period of months as the expanding debris cloud thins out and the radioactive elements decay away. But the visible display is just one aspect of a supernova's enormous energy release. The explosion ejects material at speeds of up to 30,000 kilometers per second, about 10% the speed of light. This expanding shell of debris, containing several solar masses of material, plows into the surrounding interstellar medium, creating a supernova remnant that can persist for thousands of years. Famous examples of such remnants include the Crab Nebula, formed by a supernova observed by Chinese astronomers in 1054 CE, and Cassiopeia A, the remnant of a supernova that occurred around 1680 but wasn't observed on Earth due to dust obscuration. These remnants continue to expand for thousands of years, eventually merging with the interstellar medium. During this process, they distribute the heavy elements created both during the star's life and during the supernova explosion itself. This enrichment of the interstellar medium with elements heavier than hydrogen and helium is one of the most important contributions massive stars make to galactic evolution. Elements essential for life, such as carbon, oxygen, and nitrogen, were created inside massive stars and dispersed by supernovae. Even more remarkably, elements like gold, platinum, and uranium are created through the rapid neutron capture process that occurs only in the extreme conditions of a supernova explosion. So quite literally, the gold in your jewelry was forged in the death throes of ancient stellar giants. The fate of the stellar core depends on its mass. For our 40 solar mass Hypergiant, which has lost significant mass during its lifetime through stellar winds, the collapsing core likely forms a neutron star. This is an object composed almost entirely of neutrons, with a mass greater than the Sun compressed into a sphere just 20 to 30 kilometers in diameter. The density of a neutron star defies comprehension, about 100 trillion grams per cubic centimeter. A teaspoon of neutron star material would weigh about 1 billion tons on Earth. This density approaches that of an atomic nucleus, essentially making a neutron star a single giant atomic nucleus spanning kilometers. Neutron stars have extraordinary properties beyond their density. They spin rapidly, sometimes hundreds of times per second, due to the conservation of angular momentum during core collapse. They possess magnetic fields trillions of times stronger than Earth's, capable of tearing apart atoms in their vicinity, and their surfaces have temperatures of hundreds of thousands of degrees Celsius when first formed. If the collapsing core is more massive, exceeding about 3 solar masses, not even neutron degeneracy pressure can halt the collapse. In this case, the core continues to implode until it forms a black hole, an object so dense that not even light can escape from within its event horizon. Black holes represent the ultimate fate of the most massive stars. They are regions of space-time where gravity is so strong that it curves space completely back on itself, creating a boundary, the event horizon, beyond which nothing can return to the outside universe. Despite their name, black holes are not empty voids but rather incredibly dense concentrations of mass. A black hole formed from a stellar core contains several times the mass of our Sun compressed into a singularity of effectively zero volume. This creates a region of extreme space-time curvature, surrounded by an event horizon, typically ranging from about 10 to 100 kilometers in diameter, depending on the black hole's mass and spin. The formation of a black hole during a supernova can lead to additional phenomena beyond the explosion itself. If the star is rotating rapidly, the collapsing core may form an accretion disk of material spiraling inward. Combined with the star's magnetic field, this can create jets of material and radiation blasting outward along the rotation axis at speeds approaching the speed of light. When these jets are pointed toward Earth, we observe what's called a gamma-ray burst, the most energetic regular events in the universe since the Big Bang. Lasting from milliseconds to several minutes, gamma-ray bursts release as much energy as our Sun will produce over its entire 10 billion-year lifetime. For hypergiants at the very upper end of the mass scale, even more exotic fates may await. Stars with initial masses above about 150 solar masses might experience a different kind of explosion, called a pair instability supernova. In these extraordinary events, temperatures in the core become so high, over about 3 billion degrees Celsius, that gamma rays spontaneously convert into electron-positron pairs. This sudden removal of photon pressure, which had been helping support the core, triggers a partial collapse. The resulting compression ignites runaway fusion reactions that can completely disrupt the star in a single catastrophic explosion. Unlike standard core collapse supernovae, pair instability supernovae may leave no remnant whatsoever, completely dispersing all of the star's mass into space. For stars above approximately 240 solar masses, theory suggests that collapse directly to a black hole may occur without a visible supernova, as the energy of implosion is insufficient to reverse the collapse. However, such extremely massive stars are exceedingly rare, and we have yet to definitively observe either their lives or deaths. The deaths of hypergiants are not merely spectacular events to be observed and catalogued, they are crucial drivers of cosmic evolution. The energy and material they release shape galaxies and create the conditions necessary for subsequent generations of stars and planets. The shock waves from supernovae compress nearby gas clouds, potentially triggering new rounds of star formation. The heavy elements they disperse provide the raw materials for rocky planets, water, and eventually life. And the neutron stars and black holes they leave behind can form exotic binary systems, merging in events that produce gravitational waves and create the heaviest elements in the universe. In a very real sense, we owe our existence to ancient hypergiants that lived and died billions of years ago. The iron in our blood, the oxygen we breathe, the calcium in our bones, were all created inside massive stars and scattered through space by their explosive deaths. This connection between stellar death and the ingredients for life highlights a profound cycle in cosmic evolution. Stars are born from the debris of previous stellar generations, each cycle enriching the universe with more complex elements and creating the conditions for increasingly diverse chemistry and, eventually, biology. Let's consider some specific examples of supernovae from hypergiants that have been observed in recent times. One of the most famous is SN 1987A, which appeared in the Large Magellanic Cloud, a satellite galaxy of our Milky Way, in February 1987. This was the closest observed supernova since Kepler's supernova in 1604, and the first visible to the naked eye since the invention of the telescope. SN 1987A came from a blue supergiant progenitor called Sanjilik -69°202, a star with about 20 times the mass of our Sun. Although not quite a hypergiant by our definition, this supernova provided invaluable information about the death of massive stars, including the first detection of neutrinos from a supernova, confirming theoretical models of core collapse. More recently, SN 2006 GY stands as one of the most luminous supernovae ever recorded, about 100 times brighter than a typical supernova. Its progenitor was likely a hypergiant with a mass between 100 and 130 solar masses. The explosion was so energetic that astronomers suspect it may have been a pair instability supernova, though debate continues about its exact nature. Another extraordinary event was SN 2006 JC, notable for the detection of its progenitor in archival images. The star underwent a major eruption just 2 years before exploding, suggesting that hypergiants can become increasingly unstable in their final days, experiencing significant mass loss events shortly before their final demise. These observations underscore the complex and varied ways that hypergiants can die. Some explode relatively quietly after shedding much of their mass through stellar winds. Others retain most of their mass and die in spectacular explosions, visible across cosmic distances. And some experience a series of eruptions or outbursts before their final supernova, creating complex circumstellar environments that interact with the explosion. One particularly interesting case is SN 2009 IP, which appeared to be a typical Type II supernova until astronomers noticed something unusual. The explosion seemed to be interacting with shells of material ejected by the star years to decades before it exploded. This suggests a pattern of increasing instability as the star approached its end, with multiple mass loss events preceding the final explosion. This brings us to an important question. Can we predict when a specific hypergiant will explode? The answer, at present, is no, at least not with any precision. While we can identify stars that are in the final phases of their lives and will likely explode within the next 1,000 to 100,000 years, predicting the exact timing of a supernova remains beyond our capabilities. However, there are signs that indicate a star is approaching its end. Increasing variability, major mass loss events, changes in brightness or color, and unusual spectral features can all suggest that a star is becoming unstable. Astronomers monitor known hypergiants for such changes, hoping to catch one in the act of exploding or even in the final days or hours before its demise. Betelgeuse, the famous red supergiant in Orion, created excitement in the astronomical community when it unexpectedly dimmed by about 2/3 in late 2019 and early 2020. Some speculated that this might be a precursor to a supernova, but the star subsequently returned to its normal brightness. The dimming was eventually attributed to a large dust cloud ejected from the star's surface, a reminder that hypergiants can experience significant variations without being on the immediate verge of explosion. Nevertheless, Betelgeuse is certainly in the final stages of its life. With an estimated age of about 8 to 8.5 million years, it has likely exhausted the hydrogen in its core and is currently fusing helium or possibly carbon. Astronomers expect it to explode as a supernova within the next 100,000 years, an eye blink in cosmic terms but far longer than human timescales. When Betelgeuse does eventually explode, it will be a spectacular sight from Earth. Located just over 600 light-years away, the supernova would be visible even in daylight, shining as brightly as the half-moon and casting shadows at night. Despite this brightness, it poses no danger to Earth, being far too distant for its radiation or debris to affect us significantly. Another hypergiant that astronomers watch closely is Eta Carinae, famous for its great eruption in the 1840s, when it briefly became the second brightest star in the night sky. This event wasn't a true supernova, but rather a massive outburst that ejected more than 10 solar masses of material, creating the beautiful bipolar nebula visible today. Eta Carinae is actually a binary system, with the primary star having an estimated initial mass of around 150 solar masses, placing it among the most massive stars known. After its great eruption, and subsequent mass loss, the primary may now have between 90 and 100 solar masses remaining. It's a prime candidate for a future supernova, or perhaps even a pair instability supernova, though the timing remains uncertain. The diversity of hypergiants and their deaths reminds us that stellar evolution is not a one-size-fits-all process. Each star's journey depends on its initial mass, chemical composition, rotation rate, magnetic field, and whether it has companion stars. These factors combine to create a wide range of evolutionary paths and final fates. Some hypergiants may end their lives as relatively ordinary supernovae, while others might produce exotic phenomena like gamma-ray bursts or pair instability explosions. Some may leave behind neutron stars, others black holes, and a few might disperse entirely, leaving no compact remnant at all. This diversity of outcomes from seemingly similar starting points highlights the complexity of stellar physics and the challenges in predicting the exact fate of any particular star. It's a reminder that, even with our advanced understanding of nuclear physics and stellar evolution, aspects of these cosmic processes remain incompletely understood. As our observational capabilities improve, we continue to discover new and unexpected phenomena related to the deaths of massive stars. Space-based observatories like the James Webb Space Telescope and Chandra X-ray Observatory provide unprecedented views of supernovae and their remnants, while neutrino detectors and gravitational wave observatories offer entirely new windows into the physics of stellar collapse. These observations, combined with increasingly sophisticated computer models, gradually unveil the full story of how the largest stars in the universe live and die. But many questions remain. What is the precise mechanism by which the supernova shockwave successfully propagates through a star? How exactly do rotation and magnetic fields affect the explosion? And what is the upper limit of stellar mass, beyond which stars cannot form or cannot maintain themselves, even briefly? The answers to these questions will not only satisfy our curiosity about cosmic extremes, but will also deepen our understanding of fundamental physics. The deaths of hypergiants involve conditions far more extreme than we can replicate in laboratories, making them natural experiments in nuclear physics, general relativity, and plasma dynamics. In a very real sense, each supernova we observe is a window into physics at its most extreme, a glimpse of matter and energy at the edges of what's possible in our universe. The fact that we can observe these events from billions of light years away, analyze their spectra, measure their energy output, and reconstruct the properties of their progenitor stars is a testament to the power of modern astronomy. And perhaps most profoundly, the study of stellar deaths connects us to our own cosmic origins. When we observe a hypergiant exploding in a distant galaxy, we're witnessing the same process that created many of the atoms in our bodies. The calcium in our bones, the iron in our blood, the oxygen we breathe, all had their origins in stars that lived and died long before our solar system formed. In the next chapter, we'll explore how astronomers have managed to find and measure these cosmic monsters, examining the techniques and technologies that allow us to study objects thousands or millions of light years away. Discovering and measuring the largest stars in the universe presents astronomers with extraordinary challenges. These stellar giants are rare, often obscured by dust, and located thousands or even millions of light years away. Yet through ingenious techniques and powerful instruments, scientists have managed to find these cosmic monsters and determine their true dimensions. In this chapter, we'll explore how astronomers hunt for hypergiants and how they measure their vital statistics. The search for stellar giants begins with a fundamental question. How do we find noteworthy stars among the hundreds of billions in our galaxy, let alone in more distant galaxies? The answer lies in their extreme properties. Hypergiants stand out due to their exceptional brightness, unusual spectra, and often their variability or instability. Let's start with brightness. Despite their great distances, hypergiants are among the most luminous objects in the universe. Their enormous energy output makes them visible across vast cosmic distances. A typical hypergiant might shine with the light of hundreds of thousands or even millions of suns, making it detectable even from other galaxies. Astronomers conduct systematic sky surveys, scanning large portions of the sky to catalog stars and measure their properties. Historic surveys like the Henry Draper Catalogue began this process in the late 19th century, while modern digital surveys like the Sloan Digital Sky Survey or Gaia mission have mapped billions of stars with unprecedented precision. These surveys capture basic data about each star, including its position, apparent brightness, and color. From this information, astronomers can identify candidates for further study. Stars that appear unusually bright for their color, or that show colors indicating extreme temperatures or unusual compositions, are flagged for follow-up observations. The most powerful tool for studying distant stars is spectroscopy, the analysis of light split into its component wavelengths. When starlight passes through a prism or diffraction grating, it forms a spectrum, a rainbow-like band of colors crossed by dark or bright lines. These spectral lines are the fingerprints of elements in the star's atmosphere, and their patterns tell us a wealth of information about the star's temperature, composition, rotation, and motion through space. Hypergiants have distinctive spectral signatures. Their relatively cool outer layers contain molecules that leave characteristic absorption patterns in the spectrum. At the same time, their unstable atmospheres and powerful stellar winds create unusual emission features and broadened spectral lines, indicating high-velocity gas flows. For example, red hypergiants show strong absorption bands from molecules like titanium oxide and water vapor, which can only form at relatively cool temperatures. They also show emission lines from atoms like hydrogen and calcium that have been excited by the star's radiation. The combination of these features, along with their extreme brightness, helps identify these stars as members of the hypergiant class. Once candidate hypergiants are identified, astronomers face the challenging task of measuring their actual physical properties, particularly their size. This is where the real detective work begins. The most direct way to measure a star's size would be to resolve its disk, to actually see the star as more than just a point of light. But even the largest stars appear incredibly tiny from Earth due to their vast distances. Resolving stellar disks requires specialized techniques and the most powerful telescopes available. One such technique is interferometry, which combines light from multiple telescopes to achieve resolution far beyond what any single telescope could provide. By precisely measuring the interference patterns created when light from different telescopes is combined, astronomers can determine the angular size of a star, how large it appears in the sky. The Very Large Telescope Interferometer in Chile, which combines light from four 8.2-meter telescopes, has been crucial in measuring the sizes of nearby hypergiants. For example, in 2013, astronomers used this instrument to make precise measurements of UY Scuti, determining its angular diameter to be just 0.0071 arcseconds, less than 1/2000th the apparent width of Jupiter as seen from Earth. To convert this tiny angular measurement into an actual physical size, astronomers need to know the star's distance. This introduces another layer of complexity, as measuring cosmic distances accurately is one of astronomy's greatest challenges. For relatively nearby stars, within a few thousand light-years, astronomers can use parallax, the apparent shift in a star's position as Earth orbits the Sun. By measuring this tiny shift, they can calculate the star's distance using simple trigonometry. The European Space Agency's Gaia satellite, launched in 2013, has revolutionized this field by measuring precise parallaxes for over 1.3 billion stars. But many hypergiants lie beyond the range where parallax is effective. For these more distant stars, astronomers must rely on indirect methods. One approach uses the star's apparent brightness compared to its estimated intrinsic luminosity, derived from its spectral characteristics. This method, known as spectroscopic parallax, involves considerable uncertainty, but is often the only option for very distant stars. Another complication is interstellar dust, tiny particles that permeate the spaces between stars. This dust absorbs and scatters starlight, making stars appear dimmer and redder than they actually are. Astronomers must carefully correct for this extinction effect, which can be substantial for hypergiants located in or behind dusty regions of the galaxy. Given these challenges, it's not surprising that measurements of hypergiant sizes come with significant margins of error. Different studies may report somewhat different values for the same star, and these values may be revised as observational techniques improve or new data becomes available. For instance, VY Canis Majoris, was once thought to be the largest known star, with estimates placing its diameter at up to 2,000 times that of our Sun. More recent studies have revised this figure downward to perhaps 1,200 times solar, still enormous but significantly less than earlier estimates. This revision wasn't because the star changed, but because our measurements improved. Similar refinements occur continuously as astronomers apply new techniques and gather better data. The current record holders for largest stars, objects like UY Scuti and Stephenson 2-18, may themselves be surpassed or their sizes revised as our observational capabilities advance. Beyond simply measuring size, astronomers seek to understand the complete physical nature of hypergiants. This includes determining their mass, temperature, composition, rotation rate, and mass loss rate, as well as studying their variability and any surrounding nebulae. Mass is particularly challenging to measure directly unless the star is part of a binary system. For isolated hypergiants, mass must be estimated from theoretical models that relate observable properties like luminosity and temperature to the star's mass. These estimates typically suggest that despite their enormous size, many hypergiants have lost substantial mass during their lives and may contain only 10 to 40 times the mass of our Sun. Temperature can be determined relatively accurately from the star's spectrum. The strength of various spectral lines and the overall distribution of energy across different wavelengths provide reliable temperature indicators. Most red hypergiants have surface temperatures around 3,000 to 4,000 Kelvin, much cooler than our Sun's 5,800 Kelvin, but still hot enough to vaporize any known material. Composition analysis uses the strength of spectral lines from different elements to determine the chemical makeup of the star's atmosphere. Hypergiants often show unusual abundances, with elements like nitrogen, enhanced, and carbon depleted due to the dredging up of material that has undergone nuclear processing in the star's interior. Rotation is measured through the broadening of spectral lines. As a star rotates, light from the approaching edge is blue-shifted, while light from the receding edge is red-shifted, broadening the star's spectral lines. Most hypergiants rotate relatively slowly, with periods of months or years, though their enormous size means their equators may still move at speeds of thousands of kilometers per hour. Mass loss rates can be determined by analyzing the strength and profile of certain spectral lines that form in the star's wind, or by observing the surrounding nebula and estimating how much material has been ejected over time. Hypergiants typically lose mass at rates of 1 Earth mass per year or more, creating extensive circumstellar environments. Studying the variability of hypergiants provides additional insights into their nature. Many show semi-regular changes in brightness, with periods ranging from months to years. These variations reflect pulsations in the star's outer layers or episodic mass loss events. By monitoring these changes over time, astronomers can better understand the star's structure and evolutionary state. The nebulae surrounding many hypergiants provide valuable information about their history. These clouds of ejected material record the star's mass loss over thousands of years, with different structures corresponding to distinct outburst events. High-resolution imaging of these nebulae, particularly in infrared wavelengths that can penetrate interstellar dust, reveals complex patterns that trace the star's past behavior. One of the most powerful tools for studying hypergiants is the Hubble Space Telescope, which provides sharp, detailed images from its position above Earth's atmosphere. Hubble has captured stunning views of stars like Eta Carinae, showing the complex bipolar nebula created by its great eruption in extraordinary detail. Even more recently, the James Webb Space Telescope, with its unprecedented infrared sensitivity, is providing new insights into cool, dust-enshrouded objects like hypergiants. Webb's ability to peer through dust clouds and observe in wavelengths where hypergiants emit most of their energy makes it an ideal instrument for studying these stellar giants. Ground-based telescopes continue to play crucial roles as well. Facilities like the Very Large Telescope in Chile, the Keck Observatory in Hawaii, and the Gemini observatories combine large mirror diameters with advanced adaptive optics to achieve sharp images despite the blurring effects of Earth's atmosphere. Radio telescopes offer yet another window into hypergiant behavior. By observing at radio wavelengths, astronomers can detect molecular emission from the star's extended atmosphere and surrounding nebula. The Atacama Large Millimeter Array in Chile, with its exceptional sensitivity and resolution, has been particularly valuable for studying the cool, molecule-rich environments around red hypergiants. The combination of observations across the electromagnetic spectrum, from radio to ultraviolet, provides a complete picture of these extraordinary stars. Different wavelengths probe different layers of the star and its surroundings, revealing a complex structure that no single type of observation could capture. This multi-wavelength approach has been especially valuable for studying the mysterious hypergiant VY Canis Majoris. Observations in visible light show a reddish star surrounded by an asymmetric nebula. Infrared observations reveal the full extent of the dust surrounding the star, much of it too cool to see in visible light. Radio observations detect molecules like carbon monoxide and silicon monoxide in the extended atmosphere, tracing the flow of material away from the star. Together, these diverse observations tell us that VY Canis Majoris is not just a simple spherical star, but a complex system, with the central star surrounded by arcs, knots, and filaments of ejected material stretching out over thousands of astronomical units. This complexity is typical of hypergiants and reflects their dynamic, unstable nature. The discovery of hypergiants beyond our galaxy represents another triumph of modern observational astronomy. Detecting individual stars in other galaxies is challenging due to their great distances, but the extreme brightness of hypergiants makes them visible even millions of light-years away. Telescopes like Hubble have identified individual supergiants and hypergiants in nearby galaxies like the Andromeda Galaxy and the Large Magellanic Cloud. By studying these extragalactic stellar giants, astronomers can compare their properties to those in our Milky Way and better understand how environmental factors like metallicity, the abundance of elements heavier than helium, affect stellar evolution. One exciting discovery from these extragalactic studies is that the largest stars may be even larger in environments with lower metallicity. This makes sense theoretically, as metals in a star's atmosphere enhance opacity, increasing radiation pressure and limiting growth. In metal-poor environments like dwarf galaxies or the early universe, stars might be able to accumulate more mass before radiation pressure halts their growth. The study of hypergiants connects to broader questions in astronomy and astrophysics. How do the most massive stars form? What are the upper limits of stellar mass and size? How do these extreme stars affect their surroundings and influence galactic evolution? The formation of very massive stars remains incompletely understood. Standard models of star formation suggest that radiation pressure should limit stellar masses to around 100 solar masses, yet we observe stars that appear to exceed this limit. Various theories have been proposed to explain this discrepancy, including stellar mergers, rapid accretion through dense disks that can overcome radiation pressure, and formation in particularly dense, turbulent molecular clouds. The Hubble Space Telescope has observed massive star formation in regions like the R136 cluster in the Large Magellanic Cloud, where several stars with masses over 100 solar masses appear to have formed together. These observations suggest that environmental factors play a crucial role, with the most massive stars preferentially forming in dense clusters. As for the upper limits of stellar size, theoretical models suggest that stars much larger than those we've already observed would be too unstable to exist for long periods. Stars with radii beyond about 2,000 to 2,500 times that of our Sun would likely have such tenuous outer layers that they would rapidly lose mass through powerful stellar winds, preventing them from growing larger. The influence of hypergiants on their surroundings is profound. Their intense radiation ionizes nearby gas, their powerful winds sculpt the interstellar medium, and their eventual supernovae trigger new rounds of star formation. In a very real sense, these stellar monsters drive the evolution of their host galaxies. The search for and study of hypergiants continues to advance with new instruments and techniques. Upcoming facilities like the Extremely Large Telescope, with its 39-meter primary mirror, will provide unprecedented views of these stellar giants. Future space missions will measure stellar parameters with even greater precision, potentially revealing hypergiants that remain hidden to current instruments. One particularly promising avenue is asteroseismology, the study of oscillations within stars. Just as seismologists use earthquakes to probe Earth's interior, astronomers can use stellar pulsations to investigate the internal structure of stars. Hypergiants naturally pulsate, and careful analysis of these pulsations can reveal details about their interior that would otherwise remain inaccessible. As our understanding of hypergiants grows, so too does our appreciation for their place in cosmic history. These short-lived stellar titans represent extreme cases in stellar evolution, pushing against the physical limits of what a single star can be. Their brief, intense lives and spectacular deaths play crucial roles in the chemical enrichment of the universe and the ongoing cycle of stellar birth, life, and death. In the next chapter, we'll explore another aspect of these cosmic monsters, their rarity and the special conditions needed for their formation. Why are such enormous stars so uncommon, and what can their scarcity tell us about fundamental processes in the universe? The historical journey to discovering hypergiants is a fascinating story in itself, reflecting the evolution of astronomical knowledge and technology. The first hints that stars might come in dramatically different sizes emerged in the early 20th century, as astronomers began to systematically measure stellar properties. Ejnar Hertzsprung and Henry Norris Russell independently developed what became known as the Hertzsprung-Russell diagram, a plot of stellar luminosity against temperature or color. This revolutionary visualization revealed that stars fall into distinct categories, with giants and supergiants occupying a different region of the diagram than main sequence stars like our Sun. The recognition of supergiants as a distinct stellar class came in the 1920s and 30s, with astronomers like Annie Jump Cannon developing the spectral classification system still used today. Stars designated as class Ia or Ia+, were the most luminous supergiants, what we now call hypergiants. Some of these extraordinary stars had been known since antiquity, visible to the naked eye despite their vast distances. Betelgeuse, for instance, has been observed since prehistoric times, its distinctive reddish color making it stand out in the constellation Orion. But understanding its true nature as an enormous, dying star came only in the modern era. The first direct measurement of a stellar diameter beyond the Sun came in 1920, when Albert Michelson and Francis Pease used an interferometer attached to the Mount Wilson Observatory's 100-inch telescope to measure the angular size of Betelgeuse. They found it to be about 0.047 arc-seconds, which, combined with the estimated distance, indicated a diameter hundreds of times that of our Sun. This groundbreaking measurement confirmed what spectroscopic studies had suggested, that some stars are truly enormous compared to our Sun. It marked the beginning of a new era in stellar astronomy, where stars were no longer just points of light, but physical objects with measurable dimensions. Throughout the mid-20th century, astronomers refined their understanding of stellar giants through increasingly sophisticated spectroscopic analysis. The development of infrared astronomy in the 1960s and 70s was particularly important, as many hypergiants emit most of their energy at infrared wavelengths due to their relatively cool temperatures. The 1970s saw increased interest in extreme stars like VY Canis Majoris, which was recognized as an extraordinary object by astronomers studying evolved, massive stars. However, accurate measurements of its size remained elusive due to its great distance and the obscuring effects of interstellar dust. The launch of the Hubble Space Telescope in 1990, despite its initial optical problems, eventually provided unprecedented views of stellar giants and their surrounding nebulae. Hubble's sharp images revealed the complex structures around stars like Eta Carinae in extraordinary detail, showing arcs, filaments, and shells of ejected material that told the story of the star's tumultuous history. The 21st century brought new instruments and techniques that further revolutionized the study of hypergiants. Adaptive optics systems on ground-based telescopes began to match or even exceed Hubble's resolution by compensating for the blurring effects of Earth's atmosphere. Interferometric arrays like the Very Large Telescope Interferometer provided the angular resolution needed to directly measure the sizes of distant stellar giants. In 2013, a team led by astronomer Marcus Witkowski used the Very Large Telescope Interferometer to make precise measurements of UY Scuti, determining its angular diameter and confirming it as one of the largest stars known. This work exemplifies the cutting-edge techniques used to study these cosmic monsters. The search for hypergiants faces several observational challenges. First is simply their rarity. Hypergiants represent the extreme upper end of the stellar size distribution, and the processes that create such enormous stars occur infrequently. A typical galaxy like the Milky Way might contain only a few hundred hypergiants among its hundreds of billions of stars. Second is the challenge of interstellar dust. Many hypergiants are located in or behind dusty regions of the galaxy, particularly the galactic plane where massive stars tend to form. This dust absorbs and scatters light, making accurate measurements difficult. Infrared observations can penetrate this dust, but require specialized instruments, often space-based, to avoid the absorption of infrared light by Earth's atmosphere. Third is the inherent variability of hypergiants. Unlike more stable stars like our Sun, hypergiants can change in brightness, size, and spectral characteristics over relatively short timescales. This variability means that measurements made at different times may yield different results, complicating efforts to determine the star's true properties. Despite these challenges, astronomers have developed ingenious methods to study hypergiants. One particularly valuable approach is multi-epoch, multi-wavelength observation, studying the same star repeatedly over time and across different parts of the electromagnetic spectrum. This comprehensive approach captures the star's behavior in all its complexity, revealing patterns that might be missed by more limited observations. For example, studies of the hypergiant Rho Cassiopeiae have monitored its spectrum over decades, revealing occasional dramatic cooling events where the star's surface temperature drops by over 3,000 degrees Celsius in a matter of months. During these events, the star's outer layers expand enormously, and it may eject significant amounts of mass. Without long-term monitoring, these episodic events might be misinterpreted or missed entirely. Another powerful technique is polarimetry, the measurement of the polarization of starlight. As light passes through the circumstellar environment of a hypergiant, it becomes partially polarized, with its electric field tending to vibrate in a preferred direction. The degree and direction of this polarization provide information about the density, structure, and composition of the material surrounding the star. Polarimetric studies of VY Canis Majoris, for instance, have revealed a complex, asymmetric distribution of dust around the star, suggesting that it has experienced multiple, directional mass loss events, rather than a simple spherical outflow. This asymmetry may result from the star's rotation, magnetic fields, or possible binary interactions. The advent of computational astrophysics has added another dimension to the study of hypergiants. Computer models can simulate the structure and evolution of these extreme stars, predicting observable properties that can be compared with actual observations. These models help astronomers interpret their data and understand the physical processes occurring in and around hypergiants. For example, three-dimensional hydrodynamic simulations have shown how convection operates differently in hypergiants compared to smaller stars. Instead of the numerous, relatively small convection cells seen in our Sun, hypergiants may have just a few enormous convective regions, with individual upwellings spanning distances greater than the diameter of Earth's orbit. These simulations also reveal the inherent instability of hypergiants, showing how small perturbations can grow into large-scale disturbances that may trigger mass loss events. The results help explain the observed variability and episodic mass loss that characterize these stellar monsters. As our understanding of hypergiants has grown, so too has our appreciation for their diversity. Not all hypergiants are red supergiants like UY Scuti or VY Canis Majoris. Some are yellow hypergiants like Rho Cassiopeiae or IRC, plus 10,420, occupying an intermediate temperature range. Others, like the luminous blue variables Eta Carinae and the Pistil star, are much hotter but still remarkably large and luminous. This diversity reflects different evolutionary stages and possibly different formation pathways. A massive star might begin its post-main sequence life as a blue supergiant, evolve into a luminous blue variable, then become a yellow hypergiant, and finally a red hypergiant before ending its life as a supernova. Alternatively, it might take a different path, perhaps becoming a Wolf-Rayet star that has lost its outer hydrogen layers, exposing its hot helium-rich core. The exact evolutionary tracks depend on many factors, including initial mass, rotation rate, metallicity, and whether the star has a binary companion. Untangling these various pathways and determining which stars follow which routes remains an active area of research. One particularly interesting puzzle involves the Humphreys-Davidson limit, an observed upper boundary in the Hertzsprung-Russell diagram, above which virtually no stars are found. This empirical limit suggests that stars above a certain luminosity and temperature combination cannot exist as stable objects. They either experience such powerful mass loss that they rapidly evolve to lower luminosities, or they become unstable and end their lives as supernovae. The hypergiants we observe often lie just below this limit, suggesting they represent stars that have reached the maximum possible combinations of size, temperature, and luminosity allowed by the physics of stellar structure. Their locations in the Hertzsprung-Russell diagram may tell us something fundamental about the limits of stellar existence. Another frontier in hypergiant research involves their rotational properties. Despite their enormous size, hypergiants do rotate, though typically quite slowly compared to their earlier main sequence phases. This rotation can have significant effects on their structure, mass loss, and eventual fate. Measuring rotation in hypergiants is challenging because their surface features are largely unresolved. However, spectroscopic techniques can detect the broadening of spectral lines caused by the Doppler effect as one side of the star rotates toward us and the other away. These measurements suggest that most hypergiants rotate with periods of months to years, corresponding to equatorial velocities of perhaps 10 to 20 kilometers per second. This slow rotation is somewhat surprising given that these stars began their lives rotating much more rapidly. The explanation likely involves angular momentum loss through stellar winds and the conservation of angular momentum as the star expands. As a star swells to hundreds of times its original size, its rotation must slow dramatically to conserve angular momentum, similar to how an ice skater slows their spin by extending their arms. Despite this general slowing, rotation remains important for understanding hypergiants. Even relatively slow rotation can affect the star's shape, making it slightly oblate rather than perfectly spherical. This oblateness affects the distribution of temperature across the star's surface, with the equatorial regions typically cooler than the poles, due to the effect known as gravity darkening. Rotation also influences mass loss, potentially creating latitudinal variations in stellar winds or episodic mass ejections. The bipolar nebula surrounding Eta Carinae, with its distinctive hourglass shape, may have been shaped in part by the star's rotation, which channeled mass loss preferentially along the rotational axis. For the most rapidly rotating hypergiants, the effects can be even more dramatic. Theory suggests that rotation at a significant fraction of the critical or breakup velocity, where centrifugal force balances gravity at the equator, can lead to enhanced mass loss through a mechanism known as the bi-stability jump. This phenomenon, where a small increase in rotation or luminosity leads to a dramatic increase in mass loss rate, may explain some of the observed outbursts in hypergiants. The magnetic properties of hypergiants represent another area of ongoing research. Direct measurements of magnetic fields in these stars are extremely challenging, but indirect evidence suggests that at least some hypergiants possess significant magnetism. These fields may arise from dynamo processes in the star's convective layers, similar to but vastly larger than the dynamo that generates Earth's magnetic field. Stellar magnetic fields can influence mass loss, channel stellar winds, and create structured nebulae. They may also play roles in triggering or shaping eruptions like Eta Carinae's Great Eruption. The complex, filamentary nebulae observed around some hypergiants bear similarities to structures seen in planetary nebulae known to be shaped by magnetic fields. The study of hypergiants touches on some of the most fundamental questions in stellar astronomy. What is the maximum possible size for a star? What determines the upper limits of stellar mass? How do the most extreme stars evolve and die? By observing and measuring these cosmic monsters, astronomers hope to answer these questions and refine our understanding of stellar physics at its most extreme. In the next chapter, we'll explore the rarity of hypergiants and what their scarcity tells us about the fundamental processes governing star formation and evolution. Why are such enormous stars so uncommon, and what special conditions are required to create them? In the vast cosmic ocean of stars that populate our universe, hypergiants are extraordinary rarities. While ordinary stars like our Sun exist by the billions in a typical galaxy, true hypergiants might number only in the dozens or hundreds. This extreme scarcity raises intriguing questions. Why are such enormous stars so uncommon? What special conditions must align to create these stellar monsters? And what does their rarity tell us about fundamental processes in the universe? To understand the rarity of hypergiants, we must first examine the general distribution of stellar masses throughout the cosmos. Stars form across a wide spectrum of masses, from tiny red dwarfs with less than a tenth the mass of our Sun, to blue giants with tens of solar masses. But this distribution is far from uniform. It follows what astronomers call the initial mass function, a mathematical description of how common stars of different masses are when they form. The pioneering work on the initial mass function was done by astronomer Edwin Salpeter in the 1950s, and later refined by many others, including John Scalo and Jerry Gilmore. Their research revealed a profound truth about stellar populations. Stars with lower masses are dramatically more common than stars with higher masses. This relationship follows a power law, meaning that as you consider stars of increasingly higher mass, their numbers decrease not just linearly, but exponentially. For every star like our Sun, there are many more red dwarfs with half or quarter the Sun's mass. And for every star like our Sun, there are far fewer stars with twice or 4 times its mass. By the time you reach the mass range of stars that can become hypergiants, perhaps 40 to 100 times the Sun's mass, the numbers have dwindled to extreme rarity. For roughly every 10,000 stars like our Sun, there might be just one star massive enough to eventually become a hypergiant. But what causes this strong bias toward lower mass stars? The answer lies in the physics of star formation. Stars are born when clouds of interstellar gas, primarily hydrogen, collapse under their own gravity. As the cloud contracts, it fragments into smaller clumps that will become individual stars. The size of these fragments, and thus the mass of the resulting stars, depends on complex interactions between gravity, turbulence, magnetic fields, and radiation pressure. Several factors favor the formation of many small stars rather than a few large ones. First, smaller clumps of gas are more numerous, simply as a matter of statistics. When a large cloud fragments, it naturally produces many small pieces and fewer large ones. Second, once stars begin to form within a cloud, their radiation and stellar winds heat and disperse the remaining gas, making it harder for additional mass to accumulate onto any single protostar. This process, called stellar feedback, effectively limits how massive stars can grow in typical star-forming environments. Third, radiation pressure becomes increasingly important as a protostar gains mass. The growing star's own light pushes against the infalling material, eventually creating a barrier that can halt further growth. For typical conditions in our galaxy, this barrier kicks in well before a star can reach the mass needed to become a hypergiant. Given these obstacles, how do hypergiants form at all? Astronomers believe several special conditions must coincide. First, the birthplace must be exceptionally dense and massive. The largest stars form in giant molecular clouds containing thousands of solar masses of gas concentrated in relatively small volumes. These stellar nurseries provide the raw material needed for massive star formation and the gravitational potential to overcome radiation pressure. Regions like the Tarantula Nebula in the Large Magellanic Cloud exemplify such environments. This enormous star-forming complex contains the R136 cluster, home to several stars exceeding 100 solar masses. The extreme density and turbulence in this region appear to overcome the normal limitations on stellar mass. Second, timing plays a crucial role. The most massive stars must form quickly, before stellar feedback from their smaller siblings disperses the cloud. This creates a race against time, with only those protostars that can rapidly accumulate mass reaching the highest possible masses. Third, the environment must be relatively metal-poor, at least compared to the present-day Milky Way. In astronomical terms, metals are all elements heavier than hydrogen and helium. These heavier elements increase the opacity of gas, enhancing radiation pressure and making it harder for very massive stars to form. In environments with fewer heavy elements, radiation can escape more easily, allowing protostars to grow larger before radiation pressure halts their growth. This metallicity effect helps explain why some of the most massive stars known are found in the Large Magellanic Cloud, a satellite galaxy of the Milky Way with significantly lower metallicity. It also suggests that in the early universe, when metals were much scarcer, even more massive stars might have formed, perhaps reaching several hundred solar masses. Fourth, some hypergiants may result from stellar mergers rather than forming as single stars. In dense star clusters, stars can collide and merge, creating objects more massive than could typically form through normal star formation processes. Computer simulations suggest that in the cores of young, dense clusters, multiple mergers could potentially create extraordinarily massive stars. The star, known as MI3 in the Cygnus OB2 association, may be an example of a merger product. With an estimated mass of about 150 solar masses, it's one of the most massive stars known in our galaxy. Its location in the center of a dense cluster and its unusual properties hint at a possible origin in stellar mergers. Finally, luck plays a role. Given the statistical nature of cloud fragmentation and the many factors that can interrupt accretion onto a growing protostar, the formation of hypergiants involves an element of chance. The right conditions must persist long enough for a truly exceptional star to form, something that happens only rarely even in the most favorable environments. The combination of all these factors, the need for exceptional density, rapid formation, lower metallicity, possible mergers, and a measure of statistical fortune, explains why hypergiants are so extraordinarily rare. They represent perfect cosmic storms, where multiple unusual conditions aligned to create something at the very limits of what's physically possible for a star. This rarity has important implications for our understanding of the universe. The scarcity of hypergiants means they have less impact on cosmic history than their spectacular nature might suggest. While individually impressive, they're too uncommon to dominate processes like the chemical enrichment of galaxies or the reionization of the early universe. Yet despite their rarity, hypergiants are not irrelevant. Their enormous energy output and powerful stellar winds can shape their local environments, creating bubbles or shells in the interstellar medium that extend for tens or hundreds of light years. When they finally explode as supernovae, they inject tremendous energy into their surroundings, potentially triggering new rounds of star formation. The rarity of hypergiants also makes them valuable as test cases for stellar physics. Because they exist at the extreme edge of what's possible for a star, they challenge our theoretical models and help define the limits of stellar structure. By studying these rare objects, astronomers can test their understanding of fundamental processes like nuclear fusion, energy transport, and stellar stability. Interestingly, the scarcity of extremely massive stars appears to be a universal feature observed in galaxies throughout the local universe. Whether we look at the Milky Way, the Magellanic Clouds, or more distant star-forming galaxies, we find the same pattern: many low-mass stars, fewer intermediate-mass stars like our Sun, and very few at the highest masses. This universality suggests that the initial mass function is determined by fundamental physics rather than local conditions. While the exact shape of the function may vary somewhat between different environments, the strong bias toward lower mass stars remains constant, a basic feature of how gravity, turbulence, and radiation interact to form stars. The rarity of hypergiants may also be connected to another astronomical puzzle, the upper mass limit for stars. Theoretical considerations suggest that stars above about 150 to 200 solar masses should be unstable due to the Eddington limit, where radiation pressure exceeds gravity. Yet a few stars appear to exceed this limit, raising questions about how they formed and how they maintain their structure. The most massive star currently known, R136A1 in the Large Magellanic Cloud, may have an initial mass as high as 300 solar masses, well above the theoretical limit. Its existence challenges our understanding of stellar formation and evolution, suggesting either that our models are incomplete or that this star formed through exceptional circumstances, perhaps multiple mergers in a dense cluster core. The distribution of stellar masses also has profound implications for the habitability of the universe. Low-mass stars like red dwarfs, the most common type, have lifespans measured in trillions of years, providing stable environments for potential life for timescales longer than the current age of the universe. Stars like our Sun, less common but still numerous, live for about 10 billion years, long enough for complex life to evolve on orbiting planets. But massive stars that become hypergiants live for just a few million years, far too brief for complex life to develop on any planets they might have. Their short lives and extreme radiation would make their planetary systems, if they have them at all, challenging environments for life as we understand it. This connection between stellar mass and habitability suggests that while hypergiants are spectacular, they're not ideal hosts for life. The rarity of the largest stars may actually be beneficial for the development of complex life in the universe, ensuring that most stars are smaller, more stable, and longer lived. Another aspect of hypergiant rarity involves their distribution in time. The conditions favorable for forming the most massive stars, particularly lower metallicity, were more common in the early universe. As successive generations of stars have enriched the interstellar medium with heavier elements, the formation of extremely massive stars has likely become more difficult. This suggests that hypergiants may have been somewhat more common in the distant past, perhaps playing more significant roles in the early evolution of galaxies. The first generations of stars, formed from pristine hydrogen and helium before any heavy elements existed, may have included truly extraordinary objects with masses up to 1,000 solar masses. These hypothetical population 3 stars, as astronomers call them, have never been directly observed because they all died billions of years ago. But their influence may have been profound, producing the first heavy elements and helping to reionize the universe after the cosmic dark ages that followed the Big Bang. In the present epoch, hypergiants tend to be concentrated in regions of active star formation, particularly in spiral arms of galaxies and in starburst regions where gas is compressed by galaxy interactions or other processes. This clustering reflects their formation requirements. They need dense, massive clouds that are typically found only in these active regions. Within the Milky Way, known hypergiants cluster primarily along the spiral arms, with notable concentrations in regions like Cygnus, Carina, and Scutum. These areas represent the most active star-forming regions in our galaxy, where conditions occasionally allow for the formation of the most massive stars. The rarity of hypergiants also affects our ability to study them as a class. Because each one is unique, and there are so few to observe, astronomers must piece together their evolutionary story from a limited sample. It's like trying to understand human aging by observing only a handful of individuals, each at a different age and with different genetic backgrounds. This limitation makes theoretical modeling especially important for understanding hypergiants. By simulating stellar evolution under a range of conditions, astronomers can fill in the gaps between observed examples and create a more complete picture of how these extreme stars form, live, and die. Recent advances in computational power have enabled increasingly sophisticated models of hypergiant structure and evolution. 3-dimensional simulations now capture the complex interplay between convection, rotation, and radiation in these extreme stars, revealing phenomena like giant convection cells and episodic mass loss events that can't be represented in simpler one-dimensional models. These simulations confirm what observations suggest: hypergiants exist at the edge of stellar stability. Their enormous size and luminosity place them perilously close to the Eddington limit, where the outward push of radiation threatens to overcome gravity and tear the star apart. This inherent instability is another factor in their rarity. Even if they form, they may not survive long in their most extreme states. The scarcity of hypergiants raises an intriguing possibility. Perhaps we're seeing only the tip of the iceberg, with many more hypergiants hidden from view by interstellar dust or located in distant, unexplored regions of our galaxy. As observational techniques improve, particularly in infrared and submillimeter wavelengths that can penetrate dust, we may discover additional examples of these cosmic monsters. The James Webb Space Telescope, with its unprecedented infrared sensitivity, is particularly well suited to searching for dust-enshrouded hypergiants. In the coming years, it may reveal previously unknown examples both in our galaxy and in nearby galaxies, potentially reshaping our understanding of how common these extraordinary stars truly are. Even with such advances, however, hypergiants will remain rare cosmic phenomena. Their formation requires such exceptional conditions that they can never be common objects. They represent stellar life pushed to its absolute limits, showcasing the maximum size, mass, and luminosity possible for individual stars. In the next chapter, we'll explore another aspect of these rare stellar giants, their crucial role in producing the chemical elements necessary for planets and life. Despite their scarcity, Hypergiants have profoundly influenced the composition and evolution of the universe through their short but extraordinarily productive lives. The rarity of hypergiants becomes even more apparent when we consider specific numbers. The Milky Way contains roughly 200 billion stars, yet the number of hypergiants in our galaxy likely numbers only in the hundreds. In other words, only about 1 in a billion stars reaches the extreme dimensions we've been discussing. This extraordinary scarcity makes hypergiants among the rarest stable structures in the universe. They're far less common than planetary nebulae, neutron stars, or even black holes. There are more globular clusters in the Milky Way than there are hypergiants. To put their rarity in perspective, consider this. If stars were people, and our galaxy represented the Earth's human population, there would be only 7 or 8 hypergiants among all of humanity. You would be more likely to meet an Olympic gold medalist or a billionaire than to encounter the stellar equivalent of a hypergiant. The initial mass function that governs stellar populations follows a mathematical relationship often expressed as a power law. For stars above about 1 solar mass, the number of stars decreases approximately as the inverse cube of the mass. This means that stars with twice the mass of our Sun are roughly 8 times less common, while stars with 10 times the Sun's mass are about 1,000 times rarer. By the time we reach the mass range needed to produce hypergiants, perhaps 40 to 100 solar masses initially, the numbers have become vanishingly small. According to the Salpeter initial mass function, stars in this mass range represent less than 0.00001% of all stars formed. This strong bias toward lower masses appears to be a universal feature of star formation. It's observed in nearby star-forming regions like the Orion Nebula, in more distant massive clusters like Westerland 1, and even in different galaxies like the Large Magellanic Cloud. While the exact shape of the initial mass function may vary somewhat between environments, the strong predominance of low-mass stars remains constant. The physics behind this distribution involves the complex interplay of various forces during cloud collapse and fragmentation. Gravity pulls matter together, thermal pressure pushes it apart, magnetic fields provide support against collapse, and turbulence creates density fluctuations that seed the formation of individual stars. Mathematical models of this process, such as the theory of gravo-turbulent fragmentation developed by Richard Larson and others, predict a mass distribution remarkably similar to what we observe. The prevalence of low-mass stars appears to be a natural consequence of how gravity interacts with other forces in molecular clouds. An important factor limiting the formation of very massive stars is radiation pressure. As a protostar grows, it begins to generate significant energy through gravitational contraction and eventually nuclear fusion. This energy, primarily in the form of radiation, exerts pressure on the surrounding gas and dust. For low-mass protostars, this radiation pressure is minimal and doesn't significantly impede continued growth. But as a protostar approaches about 10 solar masses, radiation pressure becomes increasingly important. By about 40 to 50 solar masses, it creates a substantial barrier to further accretion. In typical star-forming conditions, this radiation pressure effectively caps stellar masses well below what would be needed to create the most extreme hypergiants. Overcoming this barrier requires exceptional circumstances, such as very high accretion rates that can essentially overwhelm radiation pressure. Recent simulations by researchers like Mark Krumholtz and Richard Klein have shown that under certain conditions, radiation can escape through cavities or channels in the surrounding material, allowing continued accretion despite the star's growing luminosity. These simulations suggest that stars up to about 150 solar masses might form through direct accretion, though anything larger likely requires additional mechanisms like mergers. The metallicity of the star-forming environment also plays a crucial role in determining the upper mass limit. Metals, in astronomical terms, increase the opacity of gas, making it more efficient at absorbing radiation. In metal-rich environments like the present-day Milky Way, this enhanced opacity strengthens the effect of radiation pressure, making it more difficult for very massive stars to form. In contrast, metal-poor environments like the early universe or dwarf galaxies like the Large Magellanic Cloud allow radiation to escape more easily, potentially enabling the formation of more massive stars. This helps explain why some of the most massive stars known are found in the Large Magellanic Cloud, which has about half the metallicity of the Milky Way. The relationship between metallicity and maximum stellar mass has important implications for cosmic history. In the very early universe, before the first generation of stars had enriched the interstellar medium with metals, conditions may have been ideal for forming extraordinarily massive stars. These hypothetical population 3 stars, formed from pristine hydrogen and helium, might have reached masses far greater than anything we observe today. Some models suggest they could have grown to 500 or even 1,000 solar masses, creating truly monstrous objects that would have lived brief, intense lives before exploding as supernovae, or perhaps directly collapsing to black holes. While we can never observe these first-generation stars directly, as they all died billions of years ago, their legacy persists in the chemical enrichment they provided to the early universe. The metals they forged and dispersed set the stage for all subsequent generations of stars and planets. Another factor in the rarity of hypergiants is their brief lifespans. Even if they form, they exist as hypergiants for only a tiny fraction of cosmic history. A star like UY Scuti likely spent just a few million years on the main sequence as a hot blue O-type star, and may remain in its current hypergiant phase for only about 10 to 100,000 years before either shedding enough mass to become smaller or exploding as a supernova. This brief duration means that at any given time, only a small subset of the already rare massive stars exist in the hypergiant phase. It's like trying to photograph a rare butterfly that emerges from its chrysalis for just one day of its year-long life. The brevity of the phenomenon compounds its inherent rarity. The formation of hypergiants appears to be strongly clustered in both space and time. They form preferentially in massive star clusters, where gas densities and accretion rates can reach the exceptional values needed to overcome radiation pressure. And they tend to form during intense star formation episodes triggered by galaxy mergers, spiral density waves, or other disturbances that compress interstellar gas to unusual densities. One well-studied nursery for massive stars is the Westerland 1 cluster in our Milky Way. This young, dense cluster contains at least 24 stars, with initial masses above 40 solar masses, including several red supergiants, yellow hypergiants, and luminous blue variables. The cluster's extreme density, about 100,000 times that of our solar neighborhood, provided the perfect environment for forming massive stars. Similarly, the Carina Nebula hosts several of the most massive stars in our galaxy, including Eta Carinae and several O-type supergiants. This region experienced an intense burst of star formation about 3 million years ago, creating dozens of stars massive enough to potentially become hypergiants. These star-forming regions represent cosmic perfect storms, where multiple factors align to create conditions favorable for massive star formation. They are rare environments, comprising only a small fraction of a galaxy's volume and existing for only brief periods in cosmic history. The clustering of massive star formation has important evolutionary implications. When many massive stars form together, their combined stellar winds and radiation create enormous bubbles in the interstellar medium. These bubbles can trigger new rounds of star formation at their edges, where gas is compressed by the expanding shock front. This process of sequential or stimulated star formation may play an important role in the evolution of spiral galaxies like the Milky Way. Massive stars, including the progenitors of hypergiants, act as cosmic engines, converting dense molecular gas into new generations of stars and helping to regulate the overall star formation efficiency of galaxies. Recent observations have challenged traditional views about the maximum possible mass for stars. Stars like R136, a 1 in the Large Magellanic Cloud, appear to exceed the theoretical upper limits derived from the Eddington limit, with masses possibly as high as 300 solar masses. How such extreme objects form remains an open question. One possibility is that they result from mergers of already massive stars. In dense young clusters, stars may experience close encounters or even direct collisions, potentially leading to mergers. Computer simulations of cluster evolution show that under the right conditions, a series of mergers could create stars far more massive than could form through direct accretion alone. Another possibility is that these extremely massive stars form through what's called competitive accretion. In this scenario, protostars positioned at the centers of forming clusters are able to draw in gas from a much wider region than they could capture on their own, essentially stealing material that might otherwise form separate stars. This process favors the runaway growth of a few privileged protostars at the expense of their neighbors. Astronomers Kathy Clark and Ian Bonnell have developed models of competitive accretion that successfully reproduce many observed features of massive star formation, including the strong clustering of the most massive stars and their tendency to form at cluster centers. These models suggest that the most massive stars are not scaled-up versions of stars like our Sun, but rather form through a fundamentally different process that operates only in dense, clustered environments. The rarity of hypergiants also has implications for our understanding of galaxy evolution. Despite their scarcity, these extreme stars can have disproportionate effects on their surroundings due to their enormous energy output and their spectacular deaths as supernovae. The energy and momentum injected into the interstellar medium by massive stars help regulate the overall star formation efficiency of galaxies. Without this feedback, galaxies would convert gas into stars much more rapidly than observed, exhausting their gas supplies and shutting down star formation early in cosmic history. Instead, the energy from massive stars, particularly hypergiants, helps maintain the turbulence of the interstellar medium and can even drive gas outflows from galaxies. These processes create a self-regulating system where star formation proceeds at a moderate pace that can be sustained over billions of years. The rarity of hypergiants also affects the chemical evolution of galaxies. Despite their small numbers, these stars are responsible for producing a significant fraction of certain heavy elements, particularly those created through the rapid neutron capture process during supernova explosions. Elements like gold, platinum, and many rare earth metals owe their existence primarily to the explosive deaths of massive stars. In this way, the few hypergiants have influence far beyond their numbers. They're like rare but enormously productive factories, churning out critical materials that less spectacular stars cannot produce. Without them, the chemical composition of the universe would be significantly different, potentially affecting the types of planets that could form and, ultimately, the possibility of life. The extreme rarity of hypergiants makes each one a valuable object of study. Every example provides unique insights into the limits of stellar physics and the processes that create and destroy the most massive stars. For this reason, astronomers devote significant resources to studying the handful of known hypergiants in detail, using multiple observing techniques and returning to the same objects repeatedly to monitor their behavior over time. This focused attention has revealed the dynamic nature of hypergiants. Far from being static objects, they change on human timescales, experiencing variations in brightness, temperature, and mass loss rate that can be observed over years or decades. Each one tells an ongoing story of a star struggling against its own gravity and radiation, precariously balanced at the edge of stability. In the next chapter, we'll explore the critical role these rare stellar giants play in cosmic chemistry, examining how they forge the heavy elements necessary for planets and life, despite their scarcity in the stellar population. Despite their extreme rarity in the cosmic population, hypergiants and other massive stars play a disproportionately important role in the chemical evolution of the universe. They are cosmic forges, creating and distributing the heavy elements essential for planets, complex chemistry, and eventually life itself. In this chapter, we'll explore how these stellar giants transform the simplest elements in the universe into the complex periodic table we know today, and how their spectacular deaths seed the cosmos with the building blocks of worlds like Earth. To appreciate the crucial role of hypergiants in cosmic chemistry, we must first understand the state of the universe before stars existed. The Big Bang produced primarily hydrogen, with about 25% helium and trace amounts of lithium and beryllium. All heavier elements, from carbon and oxygen to gold and uranium, were essentially absent from the primordial universe. This means that the atoms that make up most of what we see around us on Earth, including our own bodies, did not exist in the early universe. They had to be created through nuclear fusion in the hearts of stars and through the extreme conditions of stellar explosions. As the astronomer Carl Sagan famously remarked, "We are quite literally made of star stuff." The process of creating heavier elements from lighter ones is called nucleosynthesis. It occurs primarily through nuclear fusion, where atomic nuclei combine to form heavier nuclei, releasing energy in the process. This fusion happens naturally in the cores of stars, where temperatures and pressures are high enough to overcome the electrostatic repulsion between positively charged nuclei. In stars like our Sun, the main fusion process is the proton-proton chain, which converts hydrogen into helium. This relatively simple reaction powers the Sun and will continue to do so for billions of years. But the proton-proton chain doesn't produce elements heavier than helium in significant quantities. More massive stars burn hotter and can access more complex fusion pathways. Stars with more than about 1.3 solar masses primarily use the CNO cycle, which also converts hydrogen to helium, but does so using carbon, nitrogen, and oxygen as catalysts. These stars have core temperatures above about 15 million degrees Celsius, compared to the Sun's 15 million degrees. But the real chemical complexity begins when stars exhaust their core hydrogen and begin fusing helium. At temperatures around 100 million degrees Celsius, helium nuclei can fuse through the triple alpha process to form carbon. This is a crucial step in cosmic chemical evolution, as carbon is the backbone of organic chemistry and essential for life as we know it. Stars like our Sun will eventually reach this stage but won't progress beyond it. After burning helium to form carbon and some oxygen, they lack the mass to compress and heat their cores sufficiently for further fusion reactions. These stars end their lives as white dwarfs surrounded by planetary nebulae, having contributed modest amounts of carbon and oxygen to the interstellar medium. It's the more massive stars, particularly those that will become hypergiants, that drive the creation of most heavier elements. With initial masses above about 8 solar masses, these stars can reach core temperatures sufficient for carbon fusion, which begins at around 800 million degrees Celsius. This process creates elements like neon, sodium, and magnesium. As these massive stars continue to evolve, they develop a layered structure, with different fusion reactions occurring in concentric shells. The core proceeds to fuse progressively heavier elements, oxygen fusing to produce silicon and sulfur at about 1.5 billion degrees, then silicon fusing to produce iron and nickel at about 3 billion degrees. Iron represents a critical juncture in stellar nucleosynthesis. Fusing elements lighter than iron releases energy, but fusing iron or heavier elements actually requires an input of energy. This means that once a massive star develops an iron core, it can no longer generate energy through fusion. Its fate is sealed, leading inevitably to a core collapse and supernova explosion. But before we reach that dramatic endpoint, let's examine the chemical contribution of hypergiants during their lives. Due to their enormous mass and luminosity, these stars process material at an astounding rate. A hypergiant might convert several solar masses of hydrogen into helium each million years, compared to the Sun's rate of about 0.006 solar masses per million years. This accelerated fusion means that hypergiants produce heavy elements much more rapidly than ordinary stars. Over its brief lifetime, a single hypergiant might generate enough carbon to form millions of Earth-like planets, enough oxygen to fill the atmospheres of billions of worlds, and enough silicon and iron to form the rocky cores of countless terrestrial planets. But there's a catch. During their lives, most of these newly formed elements remain trapped inside the star. Only through stellar winds do some of these materials escape into the surrounding space. And while hypergiants do have exceptionally powerful winds, the bulk of their chemical contribution comes not during their lives but in their deaths. When a hypergiant exhausts all possible nuclear fuel, its iron core continues to grow until it reaches about 1.4 solar masses. At this point, the core can no longer support itself against gravity, even with the quantum mechanical effect known as electron degeneracy pressure. The core begins to collapse, triggering a chain of events that culminates in a Type II supernova explosion. This explosion is one of the most energetic events in the universe, releasing in seconds as much energy as our Sun will produce in its entire 10 billion year lifetime. The extreme temperatures and neutron fluxes created during the supernova enable nuclear reactions that cannot occur during the star's life, producing many of the heaviest elements in the periodic table. These supernova reactions fall into several categories. The R process, or rapid neutron capture process, occurs when atomic nuclei are bombarded with an enormous flux of neutrons, allowing them to capture neutrons faster than they can undergo beta decay. This process creates approximately half of the elements heavier than iron, including gold, platinum, uranium, and many rare earth elements. The P process, or proton capture process, creates some of the less abundant heavy isotopes through proton capture or photodisintegration reactions. And the S process, or slow neutron capture process, which actually occurs largely during the star's life rather than in the supernova, accounts for the other half of elements heavier than iron. Together, these processes are responsible for most of the chemical complexity we observe in the universe. Without them, the cosmos would consist almost entirely of hydrogen and helium, with trace amounts of lithium and beryllium from Big Bang nucleosynthesis, and perhaps some carbon and oxygen from the death throes of lower mass stars. The role of hypergiants in this cosmic chemistry is pivotal. Due to their extreme mass, they can create and disperse far more heavy elements than ordinary stars. A single hypergiant supernova might eject several solar masses of oxygen, a solar mass or more of carbon, and significant quantities of heavier elements like silicon, sulfur, calcium, and iron, along with smaller but crucial amounts of elements like gold, platinum, and uranium. This chemical largesse is then distributed through space by the power of the supernova explosion, with ejection velocities reaching thousands of kilometers per second. The expanding shell of debris eventually merges with the interstellar medium, enriching it with newly forged elements that will eventually be incorporated into new generations of stars and planets. Astronomers can observe this process in action by studying supernova remnants, the expanding shells of gas and dust left behind after a massive star explodes. Famous examples like the Crab Nebula, formed by a supernova observed in 1054, or Cassiopeia A, from a more recent explosion around 1680, provide detailed information about the elements produced in supernovae. Spectroscopic analysis of these remnants reveals emission lines from a wide range of elements, including oxygen, neon, sulfur, argon, and iron. The distribution of these elements isn't uniform but shows complex patterns reflecting both the layered structure of the progenitor star and the dynamics of the explosion itself. The chemical fingerprint left by hypergiants extends beyond their immediate vicinity. As their ejected material spreads through the galaxy, it gradually mixes with the interstellar medium, increasing the overall metallicity of the galaxy over time. This enrichment process has been ongoing for billions of years, with each generation of stars forming from material that contains the chemical legacy of previous stellar generations. Astronomers can trace this chemical evolution by studying stars of different ages. The oldest stars in our galaxy, found primarily in the halo and in globular clusters, have very low metallicities, sometimes less than 1% of the Sun's. These ancient stars formed early in the galaxy's history, before many supernovae had enriched the interstellar medium with heavy elements. In contrast, younger stars like our Sun have much higher metallicities, reflecting billions of years of chemical enrichment by countless generations of stars, including rare but chemically productive hypergiants. Our Sun contains about 2% elements heavier than hydrogen and helium, a modest-sounding figure that nonetheless represents a crucial increase in chemical complexity compared to the primordial universe. This progressive enrichment of the cosmos with heavy elements has profound implications for the formation of planets and the potential for life. Rocky planets like Earth require substantial amounts of elements like silicon, iron, magnesium, and nickel to form their cores and mantles. These elements were vanishingly rare in the early universe and had to accumulate through multiple generations of stellar life and death before planets like ours could form. Similarly, the organic molecules that form the basis of life as we know it rely on elements like carbon, oxygen, nitrogen, phosphorus, and sulfur. These biologically crucial elements were created primarily in massive stars and dispersed by their supernovae. In a very real sense, we owe our existence to ancient hypergiants that lived and died billions of years before our solar system formed. The specific chemical contributions of different types of stars create what astronomers call the cosmic abundance pattern, the relative proportions of different elements observed in the universe. This pattern shows characteristic peaks and valleys that reflect the nuclear processes responsible for each element's formation. Elements like oxygen, neon, magnesium, silicon, and sulfur which are produced primarily through fusion in massive stars, are relatively abundant. Elements like lithium, beryllium, and boron, which are actually destroyed in stellar interiors and must be created through secondary processes like cosmic ray spallation, are comparatively rare. And elements beyond iron show a pattern of alternating abundances reflecting the details of neutron capture processes in stars and supernovae. This abundance pattern provides a fossil record of nucleosynthesis throughout cosmic history. By studying the relative proportions of different elements and isotopes in stars, meteorites, and interstellar gas, astronomers can reconstruct the chemical evolution of the universe and the specific contributions of different types of stellar sources. For example, analysis of certain heavy element ratios can distinguish between contributions from core collapse supernovae, which come from massive stars like hypergiants, and Type Ia supernovae, which involve white dwarfs in binary systems. Other isotopic signatures can identify elements created through the S process in asymptotic giant branch stars, versus those created through the R process in neutron star mergers or supernova explosions. Recent discoveries have complicated this picture somewhat. While core collapse supernovae of massive stars were long thought to be the primary sites of R-process nucleosynthesis, creating elements like gold and uranium, newer evidence suggests that neutron star mergers may be equally or more important sources of these heaviest elements. When two neutron stars spiral together and merge, the resulting explosion, called a kilonova, creates ideal conditions for the R process. The neutron-rich environment allows for the rapid buildup of heavy nuclei through successive neutron captures. Observations of the kilonova GW170817, associated with a gravitational wave detection in 2017, provided the first direct evidence of this process, showing signatures of heavy element production. What role do hypergiants play in this revised picture? Their contribution remains crucial, but multifaceted. First, they are still major producers of elements up to iron through fusion during their lives and in their supernova explosions. Second, many of them end their lives as neutron stars, providing the raw material for later neutron star mergers that produce the heaviest elements. And third, some particularly massive hypergiants may still create significant amounts of R process elements through uncommon types of supernovae, such as those with strong magnetic fields and rapid rotation that can generate neutron-rich jets. The interplay between different nucleosynthesis sources creates a cosmic chemical ecosystem where various stellar processes contribute different elements to the overall chemical evolution of galaxies. Hypergiants, despite their rarity, are keystone species in this ecosystem, producing enormous quantities of certain elements and influencing the evolution of their surroundings through their powerful winds and explosive deaths. To appreciate the full impact of hypergiants on cosmic chemistry, consider what our solar system would be like if these stellar monsters had never existed. Without the heavy elements dispersed by ancient hypergiants, the cloud that collapsed to form our sun would have contained primarily hydrogen and helium, with perhaps trace amounts of carbon and oxygen from less massive stars. Under these conditions, rocky planets like Earth, Venus, and Mars could not have formed. Without substantial amounts of iron, silicon, and other heavy elements, only gas giants similar to Jupiter and Saturn might have coalesced. And without the diverse chemistry provided by supernova enrichment, the complex organic molecules that form the basis of life would be absent. Even if some primitive form of life could arise in such a chemically impoverished environment, it would lack the rich palette of elements that Earth life employs. Iron for hemoglobin, calcium for bones, phosphorus for DNA and energy transfer, zinc, copper, and molybdenum for enzyme function. All these elements, and many more, play essential roles in terrestrial biochemistry. Their absence would severely constrain the complexity and diversity of potential life forms. In this sense, hypergiants are cosmic enablers of complexity. Through their short, brilliant lives and spectacular deaths, they transform the simple hydrogen and helium of the primordial universe into the rich diversity of elements needed for planets, chemistry, and life. They lay the groundwork for the eventual emergence of beings capable of contemplating the stars themselves. The chemical legacy of hypergiants is not just a thing of the past. This process of stellar nucleosynthesis continues today. with massive stars currently creating and dispersing heavy elements throughout our galaxy. Every year, several supernovae explode in the Milky Way, each contributing newly forged elements to the interstellar medium. Most of these supernovae go unnoticed because they occur in distant, dust-obscured regions of the galaxy, but occasionally, one happens close enough to be visible from Earth. The last such naked-eye supernova in our galaxy was Johannes Kepler's star, which appeared in 1604. But we're statistically overdue for another, and when it happens, it will provide an unprecedented opportunity to study the chemical yields of a supernova with modern instruments. In nearby galaxies, astronomers regularly observe supernovae, with several hundred detected each year. These provide valuable data on the diverse types of stellar explosions and their chemical contributions. By studying the spectra of these events, scientists can identify the elements produced and ejected, refining our understanding of stellar nucleosynthesis. The field of galactic archaeology extends this investigation to our own cosmic neighborhood. By studying the chemical compositions of stars in the Milky Way, astronomers can reconstruct the history of chemical enrichment in different regions of the galaxy. Stars effectively record the chemical state of the gas from which they formed, preserving a fossil record of nucleosynthesis throughout galactic history. This approach has revealed that chemical enrichment doesn't proceed uniformly across a galaxy. Some regions, particularly those with frequent star formation, become enriched more rapidly than quieter areas. The spiral arms of galaxies, where hypergiants preferentially form and die, show higher levels of chemical enrichment than the regions between arms. Looking toward the future, the chemical contributions of hypergiants will continue to shape the evolution of galaxies for billions of years to come. As new generations of stars form from increasingly metal-rich gas, the possibilities for planetary systems and potentially for life become ever more diverse. In our next chapter, we'll explore the tantalizing question of what it might be like to approach one of these stellar behemoths. Could we ever get close to a hypergiant? And what would we experience if we did? Throughout our exploration of hypergiants, we've discussed these stellar monsters from a safe astronomical distance, examining their properties through telescopes and theoretical models. But what if we could somehow approach one of these cosmic titans? What would we experience as we drew closer to a star thousands of times larger than our Sun? In this chapter, we'll embark on a thought experiment, a hypothetical journey to the vicinity of a hypergiant like UY Scuti, considering the practical challenges, physical dangers, and the awe-inspiring experience such a voyage would entail. Our journey begins far from the hypergiant, perhaps at a distance similar to that between Earth and the nearest star system, Alpha Centauri, about 4.3 light-years. At this range, UY Scuti would appear as an exceptionally bright star, outshining most others in the sky due to its enormous luminosity of several 100,000 suns. Even from this vast distance, it would be a notable object, perhaps comparable in brightness to Venus as seen from Earth. Already, our instruments would detect something unusual about this star. Its spectrum would reveal the characteristic absorption patterns of a cool supergiant, with strong bands from molecules like titanium oxide that can only exist at relatively low stellar temperatures. Its infrared emission would be particularly strong, reflecting its enormous size and relatively cool surface. As we move closer, reducing the distance to perhaps 1 light-year, the star begins to show its true nature. It now outshines all other objects in the sky, except for any nearby stars. Through a telescope, we might begin to resolve its disk, appearing not as a mere point of light, but as a tiny reddish circle. Surrounding this visible disk, our infrared instruments would detect a much larger, tenuous envelope of dust and gas ejected by the star's powerful winds. At this distance, we would also begin to notice the star's variability. Over periods of months, its brightness would fluctuate noticeably as the star pulsates, expanding and contracting in its characteristic unstable manner. These brightness changes would be accompanied by shifts in color, with the star appearing redder when dimmer and more orange when brighter. Moving closer still, to about 0.1 light-years, or about 6,000 astronomical units, the star now dominates the sky, outshining all other objects combined. Its apparent diameter is still small to the naked eye, similar perhaps to how Jupiter appears from Earth, but its brightness is exceptional, casting shadows and providing significant illumination to our spacecraft. At this distance, we might encounter the outer reaches of material ejected by the star over many thousands of years. This nebulous matter, consisting of dust grains and molecules like carbon monoxide, water, and silicon monoxide, forms an extended cocoon around the hypergeant. Our spacecraft might need to navigate carefully through this material, which, while extremely tenuous, extends for trillions of kilometers. The radiation environment is also becoming more intense. The star's light, particularly in infrared wavelengths, is now strong enough to heat exposed surfaces of our spacecraft significantly. Radiation shielding becomes increasingly important to protect both instruments and any biological passengers from the growing flux of photons and charged particles from the stellar wind. As we continue our approach to within about 10 astronomical units, roughly the distance of Saturn from our Sun, the experience becomes truly otherworldly. The hypergeant now appears as a distinct disk with an apparent diameter dozens of times larger than the Sun or Moon as seen from Earth. It fills a significant portion of the sky, a vast, glowing reddish-orange presence that dominates our field of view. The light from the star at this distance would be bright enough to read by, despite its relatively cool temperature. The color would be distinctly reddish-orange, noticeably different from the yellowish-white light of our Sun. This illumination would create an alien quality to the visual experience, with all objects bathed in this unusual light. Temperature regulation for our spacecraft now becomes a critical concern. Despite the star's relatively cool surface of about 3,400 Kelvin, its enormous size means it radiates vast amounts of energy. At 10 astronomical units, the heat received would be roughly comparable to Earth's distance from the Sun, enough to heat the spacecraft to hundreds of degrees without proper thermal management systems. The stellar wind, a continuous outflow of material from the star's surface, becomes increasingly significant as we draw closer. At this distance, we encounter a flux of charged particles and dust grains moving outward at speeds of tens of kilometers per second. While much less dense than the solar wind experienced near Earth, the stellar wind from a hypergeant contains significantly more mass, including heavier elements created in the star's interior and dredged up to its surface. Our instruments detect complex molecules in this outflow, including various carbon compounds, silicates, and metal oxides. These are the building blocks of interstellar dust, created in the atmosphere of the hypergiant and blown outward by radiation pressure. We are witnessing, in real time, the process by which hypergiants enrich the interstellar medium with heavy elements. Now let's venture even closer to about 1 astronomical unit, the distance between Earth and the Sun. At this range, the experience becomes truly overwhelming. The hypergeant fills much of the sky, an immense, softly glowing wall of light that extends about 40 degrees in every direction from the center of our field of view. That's about 80 times the apparent diameter of the Sun or Moon, as seen from Earth. The visual experience would be unlike anything humans have ever encountered. Rather than a distinct, brilliant disk like our Sun, a hypergeant at this distance would appear more like an enormous, gradient wall of light. The edge of the star would appear distinctly dimmer than the center due to an effect called limb darkening, where we look through more of the star's cooler, outer atmosphere near the edges. The surface would not appear smooth, but would show subtle variations in brightness and color, reflecting enormous convection cells where hotter material rises from below and cooler material sinks. These cells, each potentially larger than our entire solar system, would create a mottled appearance visible even to the naked eye. Surrounding the main disk, we would see a much larger, far more tenuous halo of glowing gas, the star's extended atmosphere transitioning gradually into the surrounding nebula. This region, too large to take in all at once, would show complex structures, perhaps including arcs or filaments from previous mass loss events. The radiation at this distance becomes dangerous and potentially lethal without extraordinary shielding. While the star's surface temperature is cooler than our Sun, its enormous size means the total energy received is many times greater. Any exposed surface facing the star would rapidly heat to incandescent temperatures. Surprisingly, despite this intense radiation, the gravity at this distance would be quite weak. A hypergeant like UY Scuti, while physically enormous, might have only about 10 times the mass of our Sun. This mass, spread over a volume trillions of times larger, results in a very low average density and a correspondingly weak gravitational pull at large distances from its center. The most serious hazard at this distance might be episodic mass ejections. Hypergiants are highly unstable stars that occasionally expel significant amounts of material in eruption events. If our spacecraft encountered one of these mass ejections, it could be damaged or destroyed by the high-velocity gas and dust, even though the density of this material would be extremely low by terrestrial standards. Could we venture even closer, perhaps to within the orbit of Mercury, or even to the star's defined photosphere? The answer, with any technology we can currently imagine, is no. The radiation environment would become so intense that no known material could withstand it. Any conventional spacecraft would be vaporized long before it reached the star's surface. Even if we could somehow shield against the radiation, we would face the practical problem of defining where the star's surface actually begins. Unlike our Sun, with its relatively well-defined photosphere, a hypergiant's outer boundary is gradual and diffuse. The gas thins out progressively, with no clear demarcation between star and not star. If we could somehow penetrate to what astronomers define as the photosphere, the layer where the optical depth equals 2/3, we would find ourselves in an environment utterly alien and hostile to any form of matter as we know it. The gas would be incredibly tenuous by terrestrial standards, perhaps comparable to the best vacuum we can create on Earth, yet hot enough to dissociate any molecules and ionize most atoms. This combination of extreme heat and low density creates conditions unlike anything on Earth. The mean free path of particles, the average distance they travel between collisions, would be enormous, perhaps kilometers or more. This means that despite the extreme heat, convective heat transfer would be very inefficient. An object placed in this environment would receive heat primarily through radiation rather than through contact with the thin gas. The dynamics of the star's outer layers would be visible as enormous rising and falling currents of plasma, moving at speeds of perhaps tens of kilometers per second. These convective flows, bringing energy up from below and cooled material back down, create the complex surface patterns visible from a distance. Occasionally, we might witness more dramatic events like photospheric eruptions, where instabilities in the star's tenuous outer layers lead to the ejection of material at speeds exceeding the star's escape velocity. These events, driven by the enormous energy flux from below, overcoming the weak surface gravity, contribute to the star's continual mass loss. While a physical journey to a hypergiant's surface is beyond our technological capabilities, modern astronomy allows us to study these stellar monsters in remarkable detail from the safety of Earth and Earth orbit. Techniques like interferometry effectively allow us to resolve features on the surfaces of nearby supergiants like Betelgeuse, revealing the enormous convection cells and asymmetric brightness distributions. Spectroscopic observations provide detailed information about the temperature, composition, and dynamics of hypergiant atmospheres. By analyzing the positions and strengths of thousands of spectral lines, astronomers can determine not just what elements are present, but also their relative abundances, ionization states, and velocities. Infrared and submillimeter observations pierce the veil of interstellar dust to reveal the extended atmospheres and circumstellar environments of hypergiants. These longer wavelength observations are particularly valuable for studying the coolest, most extended hypergiants, which emit most of their energy in the infrared. Perhaps most excitingly, future facilities like the Extremely Large Telescope, with its 39-meter primary mirror, or space-based interferometers combining the light from multiple telescopes, may eventually provide direct images of hypergiant surfaces, showing details comparable to what a spacecraft a few astronomical units away might see. While we may never physically approach a hypergiant, our intellectual journey to understand these extreme stars continues to advance. Each new observation and theoretical model brings us closer to comprehending these cosmic monsters in all their complexity. The hypothetical journey we've described highlights several important aspects of hypergiants that are difficult to grasp from a purely theoretical description. First is their sheer visual dominance when viewed from any reasonable proximity. A star thousands of times larger than our Sun would create a visual experience unlike anything in human experience, filling a large portion of the sky with its glowing presence. Second is the gradual nature of their boundaries. Unlike terrestrial objects or even other astronomical bodies like planets, hypergiants don't have clear edges. They transition gradually from what we might consider the star proper, to an extended atmosphere to a surrounding nebula of ejected material. This continuum challenges our intuitive notions of where an object begins and ends. Third is the extreme nature of their physical conditions. The combination of high temperature and low density in their outer layers creates an environment utterly hostile to matter as we know it, yet governed by the same physical laws that operate on Earth. Understanding these extreme conditions stretches our comprehension of familiar physics to its limits. Fourth is their dynamic, ever-changing nature. A hypergiant is not a static object, but a seething, pulsating entity, continuously losing mass and occasionally experiencing more dramatic eruptions. Any journey to its vicinity would reveal not just a large star, but an active, evolving system that includes the surrounding nebula and everything affected by the star's enormous energy output. The practical impossibility of physically approaching a hypergiant also reminds us of the vast scales and extreme conditions that exist in our universe. Even with the most advanced technology we can envision, some cosmic phenomena remain forever beyond direct human experience. We can study them, understand them mathematically, even visualize them through computer simulations, but we cannot touch them or see them with our own eyes from close range. This limitation, far from diminishing our scientific journey, enhances our appreciation for what astronomy and astrophysics have achieved. Through the careful application of physics and the ingenious development of observational techniques, we can know in remarkable detail objects that we can never visit. We can measure the sizes, masses, temperatures, and compositions of stars trillions of kilometers away, and even understand the nuclear reactions occurring in their cores. Our hypothetical journey also highlights the perspective-changing nature of astronomical knowledge. From Earth, stars appear as mere points of light, their true nature and scale hidden by distance. Only through science do we recognize them as enormous, powerful objects that dwarf our planet and even our entire solar system. This changed perspective, this recognition of the true scale and nature of cosmic objects, is one of astronomy's greatest gifts to human understanding. As we conclude our imaginary voyage to the vicinity of a hypergiant, we're left with a deeper appreciation for these cosmic titans. Their enormous size, while impossible to experience directly, becomes more comprehensible when imagined from progressively closer vantage points. The hypergiant transforms from a bright point of light to a dominating presence that fills the sky, a transformation that mirrors our growing scientific understanding of these extraordinary stars. In our final chapters, we'll step back from the specific properties and behaviors of hypergiants to consider their broader significance. What do these extreme stars tell us about the limits of stellar physics? How do they fit into the grand narrative of cosmic evolution? And what aesthetic and philosophical insights might we draw from contemplating these largest of all stars? To make our hypothetical journey more concrete, let's consider what instruments on our spacecraft might detect as we approach the hypergiant. Radiation sensors would register increasing fluxes across the electromagnetic spectrum, with particularly strong signals in infrared wavelengths. Mass spectrometers would detect an increasing density of atoms and molecules in the surrounding space, primarily hydrogen, but with traces of heavier elements and even complex molecules produced in the star's cool outer atmosphere. Magnetometers would measure the strength and structure of the hypergiant's magnetic field, while weaker per unit area than the Sun's field due to the star's slower rotation and more diffuse surface. The sheer size of the hypergiant means its magnetosphere likely extends far into space, creating complex interactions with the surrounding interstellar medium. Gravitational instruments would register the star's mass, allowing us to map its distribution. Unlike smaller, denser stars where mass is highly concentrated toward the center, a hypergiant's mass is spread over an enormous volume, with a relatively low density gradient between core and outer layers. As we continue our approach, perhaps venturing to within 1/10 of an astronomical unit of the star's nominal surface, the environment becomes even more extreme. At this distance, roughly 4 times the radius of Mercury's orbit around our Sun, the hypergiant fills more than half the sky. Looking toward the star is like facing an infinite wall of glowing gas that extends beyond our peripheral vision in all directions. The radiation intensity at this distance would exceed anything in our solar system. Without extraordinary shielding, temperatures inside our spacecraft would rapidly rise to lethal levels. The cabin would fill with a diffuse, reddish-orange light filtering through any viewport, creating an otherworldly environment unlike anything experienced on Earth. Interestingly, the gravitational pull at this distance would still be relatively modest. A hypergiant, like UY Scuti, despite its enormous size, has a mass perhaps only 10 to 20 times that of our Sun. At a distance of tens of millions of kilometers from its center, the gravitational acceleration would be comparable to, or even less than Earth's surface gravity. This combination of intense radiation, but relatively weak gravity, is characteristic of hypergiants and relates directly to their tenuous nature. Their matter is spread so thin over such vast volumes that their gravitational pull at any significant distance from the center is much weaker than one might intuitively expect given their visual dominance. Could a planet actually orbit at this distance from a hypergiant? Surprisingly, the answer is theoretically yes, but with major caveats. The orbital period would be determined by the star's mass rather than its size, so a planet at this distance might complete an orbit in a matter of weeks. However, several factors make such an orbit practically impossible for any conventional planet. First, the intense radiation would vaporize any rocky or gaseous world, stripping away its atmosphere and eventually its entire mass. Second, the hypergiant's strong stellar wind would create enormous drag on any orbiting body, causing its orbit to decay rapidly. And third, hypergiants are so short-lived in their most extended phase that there simply isn't time for stable planetary systems to develop. If we could somehow protect our hypothetical spacecraft from the intense radiation and venture even closer, perhaps to within the orbit of our Sun's Mercury, we would begin to notice something remarkable. The apparent brightness of the hypergiant's surface would begin to diminish. This counterintuitive effect occurs because we're now close enough that we're seeing only a small portion of the star's surface at any given time, and that surface has a relatively low brightness per unit area due to its cool temperature. In fact, the surface brightness, the amount of energy emitted per square meter of a red hypergiant like UY Scuti, is only about 1/10,000th that of our Sun. It's only the hypergiant's enormous surface area, millions of times greater than the Sun's, that makes its total luminosity so high. This low surface brightness means that if we could somehow transport a small piece of UY Scuti's photosphere to our laboratory, it would glow with a dull red color, far less bright than an equivalent piece of our Sun's surface, which would be blindingly bright. The hypergiant's fearsome total energy output comes from its size, not its intensity per unit area. As we move even closer to the hypergiant, perhaps to within just one solar radius of its nominal surface, we enter a region where the distinction between star and surrounding space becomes increasingly blurred. The gas density increases gradually, with no sharp boundary. We are technically inside the star's extended atmosphere, though the density remains extraordinarily low by terrestrial standards. This region, sometimes called the extended photosphere or molecular sphere, has unique properties. Cool enough for certain molecules to form, but hot enough to excite them vibrationally and rotationally. It produces distinctive spectral features that astronomers use to study hypergiants from afar. Water vapor, carbon monoxide, titanium oxide, and various metal hydroxides exist in this rarefied zone, creating absorption bands in the star's spectrum. These molecules couldn't survive closer to the star's core, where temperatures dissociate them into their atomic components, nor could they form in the hotter atmospheres of smaller stars. The dynamics in this region are complex and turbulent. Enormous convection cells bring energy up from below, while cooling material sinks back down. Shock waves propagate through the tenuous gas, compressing and heating it as they pass. Localized magnetic fields create structured flows and possibly contribute to the mass loss process. If our impossibly heat-resistant spacecraft could survive here, we would witness a constantly changing environment of glowing gas, moving in vast, slow currents, and occasionally erupting outward in more energetic events. The gas would be so diffuse that even at these relatively small distances from the center, we could still see through hundreds of thousands of kilometers of it, creating the visual impression of being inside an infinite, glowing fog. The physics in this environment differs from anything we experience on Earth. The mean free path of particles, the average distance they travel between collisions, could be hundreds of meters or more. This creates a situation where conventional fluid dynamics breaks down, and the gas behaves in ways that would seem alien to our terrestrial intuitions. For instance, sound waves would propagate at velocities of several kilometers per second due to the high temperature, but would be quickly damped out due to the low density. Convection would operate on enormous scales, with individual cells potentially larger than our entire solar system. And radiation would travel enormous distances before being absorbed or scattered, creating complex patterns of energy transport that differ fundamentally from those in denser stars like our Sun. At these distances, we would also begin to detect significant outflow velocities as material escapes from the star's weak surface gravity. The tenuous gas of the extended atmosphere is gradually transitioning to a stellar wind, flowing outward at speeds of tens of kilometers per second. This continuous mass loss shapes the star's evolution and creates the complex circumstellar environment we observed from farther away. Let's pivot our thought experiment slightly. Rather than approaching a hypergiant directly, imagine we're observing from a hypothetical planet, orbiting a smaller companion star in a binary system with the hypergiant. This scenario, while still physically challenging for the reasons mentioned earlier, provides an interesting perspective on how these stellar giants might appear in a more stable viewing context. From such a vantage point, perhaps dozens or hundreds of astronomical units from the hypergiant, the enormous star would be a permanent fixture in the sky. Depending on the orbital configuration, it might rise and set like our Sun, or it might remain visible continuously from certain locations on the planet. The visual impact would be stunning. Even at a distance of 100 astronomical units, the hypergiant would appear many times larger than our Sun or Moon, as seen from Earth. Its reddish-orange glow would provide significant illumination, potentially creating a day-night cycle dominated by the differing colors of the companion star and the hypergiant. Over periods of months or years, inhabitants of this hypothetical world would notice the hypergiant changing in brightness and possibly in size. These variations, resulting from the pulsations and instabilities inherent to hypergiants, would be clearly visible to the naked eye. The star might fade by 50% or more during its dimmer phases, dramatically altering the illumination of the planet. More dramatically, such observers might occasionally witness major mass loss events from the hypergiant. A significant eruption could create a visible brightening, followed by the appearance of an expanding shell of material moving away from the star. Over decades or centuries, these repeated eruptions would create the complex nebula structures we observe around real hypergiants. The night sky on such a world would be dominated by the glow of the hypergiant and its surrounding nebula. Depending on the orientation, the ejected material might create stunning visual structures, perhaps resembling the beautiful nebulae we observe with our telescopes, but filling a large portion of the sky rather than appearing as tiny, distant objects. Such a perspective helps us appreciate that hypergiants are not just objects to be studied scientifically, but also sources of potentially transcendent visual experiences. If intelligent life could exist in proximity to these stellar titans, the spectacle would likely inspire art, mythology, and scientific inquiry just as the night sky has done throughout human history on Earth. Returning to our hypothetical direct approach to a hypergiant, let's consider one more perspective. What if we could somehow observe from the surface of a planet being engulfed as the star expands to become a hypergiant? This scenario has likely played out countless times in our galaxy's history as stars evolve and swell to enormous sizes. As the star expanded over thousands of years, the planet's environment would change dramatically. Temperatures would soar as the star's apparent size in the sky increased. Oceans would boil away, atmospheres would be lost to space, and surfaces would begin to melt as temperatures reached hundreds or thousands of degrees. In the final stages, as the star's tenuous outer atmosphere engulfed the planet, conditions would become even more extreme. The diffuse stellar material would create drag on the planet's orbit, causing it to spiral inward. Simultaneously, the enormous heat would begin to vaporize the planet's surface directly into space. Depending on the planet's mass and composition, it might survive as a core remnant for some time as it spiraled through the star's outer layers. Eventually, however, it would be completely vaporized, its material mixing with the star's atmosphere and contributing a tiny amount to its overall composition. This scenario, while catastrophic for any planet involved, actually plays an important role in our understanding of stellar composition. When astronomers detect unusual elemental abundances in a star's atmosphere, particularly lithium or refractory elements that shouldn't normally be present in the outer layers, one possible explanation is the relatively recent accretion of planetary material. For instance, a star that shows unusually high levels of elements like titanium, aluminum, or calcium in its outer atmosphere might have engulfed a rocky planet within the astronomically recent past, perhaps within the last few million years. These chemical signatures provide clues to the histories of stellar systems and the fate of their planets. Our hypothetical journey to a hypergeant illustrates several key points about these extraordinary objects. First, their sheer scale creates experiences and environments unlike anything else in the cosmos. Second, they exist at the edge of stellar stability, with structures and behaviors that challenge our understanding of stellar physics. And third, despite being fascinating scientific targets, they represent environments fundamentally hostile to human exploration, accessible only through remote observation and theoretical modeling. In the next chapter, we'll explore the aesthetic and philosophical dimensions of hypergeants, examining what these cosmic extremes tell us about the nature of the universe and our place within it. Beyond their scientific fascination as extreme astrophysical objects, hypergeants invite us to contemplate broader questions about the nature of the universe and our place within it. These stellar monsters, existing at the edge of what's physically possible for a star, reveal something profound about cosmic processes, the interplay of forces that shapes our universe, and perhaps even the meaning we find in contemplating such objects. In this chapter, we'll explore the aesthetic, philosophical, and even spiritual dimensions of the largest stars in the universe. Let's begin with the aesthetic aspect, the sheer beauty and sense of awe these objects can inspire. Even from our distant vantage point on Earth, the visible supergiants in our night sky have captivated human attention for millennia. Betelgeuse, with its distinctive reddish hue, was named by ancient Arabic astronomers and features in the mythology of cultures around the world. Antares, another red supergiant visible to the naked eye, derives its name from ancient Greek meaning rival of Ares or rival of Mars, due to its similar reddish color to the planet. These visible giants hint at the more extreme hypergeants that lie beyond naked eye visibility. When we see images of stars like VY Canis Majoris or UY Scuti, typically rendered through artistic interpretation rather than direct imagery, we confront objects of both tremendous beauty and almost incomprehensible scale. The nebulae surrounding many hypergeants, captured by telescopes like Hubble, reveal intricate structures of glowing gas and dust shaped by the star's outflows, creating some of the most visually stunning astronomical objects known. This visual beauty connects to a deeper aesthetic appreciation of cosmic processes. The complex, flowing structures in hypergeant nebulae aren't just visually appealing, they're records of physical processes operating at extremes. We're seeing the interplay of gravity, nuclear fusion, radiation pressure, and magnetohydrodynamics manifested in forms that can trigger our aesthetic sense. There's a kind of natural artistry in how fundamental physical laws, operating at stellar scales, create structures that human minds find beautiful. The philosopher Immanuel Kant distinguished between the beautiful and the sublime, with the latter characterized by greatness beyond comparison and a kind of pleasurable terror. Hypergeants certainly qualify as sublime in the Kantian sense. Their scale transcends ordinary experience, creating a cognitive tension between our ability to calculate their dimensions mathematically and our inability to truly comprehend such scales intuitively. This sublimity is enhanced by the dynamic nature of hypergeants. These aren't static objects but pulsating, mass-ejecting systems that change over human timescales. The Great Eruption of Eta Carinae in the 1840s, when this hypergeant briefly became the second brightest star in Earth's night sky, represents a moment when the sublime nature of these objects became briefly visible to ordinary human perception. Moving beyond aesthetics to broader philosophical implications, hypergeants illustrate several profound concepts. First is the principle that the universe explores all physical possibilities allowed by its fundamental laws. If stars can exist with diameters over 1 billion kilometers, the universe will produce such stars, however rarely. Hypergeants represent one extreme of the parameter space of stellar structure, showing that cosmic processes naturally explore the full range of what's physically possible. This principle extends throughout nature, from the smallest subatomic particles to the largest cosmic structures. The universe doesn't just create average, typical objects, but explores extremes in all dimensions, maximum sizes, temperatures, densities, luminosities. Hypergiants are one manifestation of this principle, showcasing the maximum size a coherent, gravitationally bound ball of plasma can achieve under the laws of physics as we understand them. Another philosophical insight offered by hypergiants concerns the relationship between stability and extremity. Hypergiants exist at the very edge of stellar stability, continuously shedding mass and occasionally experiencing dramatic eruptions. Their enormous size comes at the cost of living on a knife edge of equilibrium, where small perturbations can trigger major restructuring events. This pattern, where the most extreme expressions of a phenomenon exist in a precarious balance that cannot be maintained indefinitely, appears throughout nature. From subatomic particles to biological species to stellar giants, pushing to extremes often means sacrificing stability and longevity. Hypergiants typify this principle, achieving their extraordinary size at the cost of existing in that state for only a cosmic eye blink. The brief lives of hypergiants also illuminate the relationship between time and scale in cosmic processes. The largest stars live the shortest lives, a counterintuitive fact that reflects fundamental principles of stellar physics. A hypergiant might exist for only a few million years, compared to the trillion-year potential lifespan of the smallest red dwarfs. This inverse relationship between size and longevity reminds us that the universe operates on many timescales simultaneously, from the microsecond lives of certain particles to the trillion-year futures of the smallest stars. For human observers, this creates an interesting situation. The most spectacular stellar objects are also the most fleeting, meaning that in any given epoch of cosmic history, we see only a small sample of all the hypergiants that have ever existed or will exist. Our particular moment in cosmic time allows us to observe a few dozen of these stellar monsters, a privilege not available at all times and places in the universe's history. This temporal aspect of hypergiants connects to broader questions of cosmic evolution. These stars represent a phase in the universe's development, a time when enough heavy elements have accumulated to allow their formation, but before these elements become so abundant that they limit stellar growth through enhanced radiation pressure. Like all complex structures in the cosmos, hypergiants have their season, a window of cosmic history in which conditions favor their existence. The rarity of hypergiants also invites philosophical reflection. In a universe containing roughly 1 billion trillion stars, only a tiny fraction reach the dimensions we've been discussing. This scarcity raises questions about how we value cosmic phenomena. Does the rarity of hypergiants make them more significant, more worthy of attention than more common objects? Or does their limited impact on cosmic evolution due to their scarcity make them mere curiosities, interesting but ultimately less important than the vastly more numerous smaller stars? Different philosophical traditions might answer this question differently. A utilitarian perspective might emphasize the greater collective impact of the much more common lower mass stars, which contain more of the universe's stellar mass in aggregate. A romantic viewpoint might instead value the hypergiants precisely for their rarity and extremity, seeing them as particularly meaningful expressions of cosmic possibility. Perhaps the most balanced view recognizes that both perspectives have validity. The universe creates both the common and the rare, the average and the extreme, and a complete understanding requires appreciating both. Hypergiants, while numerically insignificant, tell us something important about stellar physics at its limits, just as more typical stars reveal the standard pathways of stellar evolution. The study of hypergiants also illuminates the human capacity for understanding phenomena far beyond direct experience. No human will ever approach a hypergiant, feel its heat, or see its surface with their own eyes. Yet through science, we can know these objects in remarkable detail, measuring their properties, understanding their internal structures, and even predicting their future evolution. This ability to comprehend the unreachable represents one of humanity's most impressive cognitive achievements. Using the tools of mathematics, physics, and astronomy, we extend our understanding far beyond the scales and environments we can directly experience. The fact that we can meaningfully discuss objects trillions of kilometers away, with sizes billions of times larger than ourselves, demonstrates the power of the scientific method to transcend the limitations of our physical senses. At the same time, the gap between intellectual understanding and intuitive comprehension of hypergeance reminds us of our cognitive limitations. We can calculate the volume of Uy Scuti precisely, noting that it could contain 5 trillion suns. But can we truly grasp what that means? The number registers intellectually, but the reality it represents exceeds our intuitive capacity for understanding. This tension between what we can calculate and what we can intuitively comprehend appears throughout modern science, from quantum mechanics to cosmology. Hypergeans provide a particularly clear example, being objects that we can mathematically describe with precision but cannot truly visualize or intuitively grasp. They remind us that our evolved cognitive apparatus, designed for dealing with medium-sized objects moving at moderate speeds, struggles with the true extremes of the cosmos. The Hypergeans also connect to ancient philosophical questions about limits and boundaries. Where exactly does a Hypergean end and surrounding space begin? As we've discussed previously, the boundary is gradual rather than sharp, with density decreasing progressively with distance from the center. This challenges our intuitive notion of objects as having well-defined edges and raises questions about how we define the boundaries of cosmic structures. Similar questions arise throughout astronomy, from the boundaries of galaxies to the edge of our observable universe. The hypergiants, with their diffuse outer layers and surrounding nebulae of ejected material, exemplify this philosophical problem of boundaries. They remind us that many natural boundaries are conventions rather than absolute divisions, useful for human understanding, but not necessarily reflecting sharp discontinuities in nature itself. For many people, contemplating objects of such immense scale evokes spiritual or religious feelings. The enormous gulf between human and hypergean scales can trigger a sense of cosmic humility, a recognition of our physical insignificance compared to the largest objects in the universe. This feeling, which has been called the overview effect, when experienced by astronauts viewing Earth from space, can prompt profound shifts in perspective about humanity's place in the cosmos. Different religious and spiritual traditions might interpret this feeling in various ways. Some might see hypergeans as manifestations of divine creative power, expressions of the grandeur of creation that point toward a transcendent reality beyond the physical universe. Others might find in these stellar giants a purely natural sublimity, awesome in its scale, but arising from the same physical laws that govern all cosmic processes. Either way, the emotional and psychological impact of contemplating such objects seems universal. Human minds respond to extremes of scale, beauty, and power with a characteristic mixture of awe, wonder, and perhaps a touch of existential vertigo. The largest stars trigger this response particularly strongly, their sheer enormity challenging our sense of cosmic significance. Yet alongside this potential for inducing humility, hypergeans also testify to the remarkable capabilities of the human mind. The fact that beings as small and physically fragile as humans can discover, measure, and understand objects as vast and powerful as hypergeans represents an extraordinary cognitive achievement. There's a kind of cosmic symmetry in how creatures occupying a tiny portion of a small planet can comprehend the largest single objects in the universe. This symmetry suggests that while humans may be physically insignificant on cosmic scales, our capacity for understanding grants us a different kind of significance. We are, as far as we know, the portion of the cosmos that has become conscious of itself, able to discover and appreciate phenomena like hypergeans. In our comprehension of these stellar monsters, the universe achieves a kind of self-knowledge. The relationship between hypergeans and life offers another philosophical dimension to consider. As we've discussed in earlier chapters, the heavy elements created and dispersed by massive stars, including hypergeans, provide the raw materials for planets and eventually for life. Without the chemical enrichment provided by generations of massive stars, Earth and its biosphere could not exist. This creates an interesting connection between the most extreme stellar objects and the phenomenon of life. Hypergeans, despite being environments utterly hostile to life, play a role in creating the conditions necessary for life elsewhere in the cosmos. Their brief, intense existence and spectacular deaths contribute to the chemical diversity needed for the emergence of complexity in other settings. This relationship exemplifies a broader pattern in cosmic evolution, where processes occurring at one scale or in one environment enable developments at different scales or in different environments. The universe operates as an interconnected system, with energy and matter flowing between different types of structures and enabling increasingly complex forms of organization over cosmic time. Hypergiants, representing one extreme of stellar structure, form part of this cosmic network. Their contributions to nucleosynthesis and interstellar enrichment connect them to the overall evolutionary trajectory of the universe, from the simplicity of the early cosmos to the complexity of galaxies, planetary systems, and potentially life. As we reflect on the largest stars known, we might also consider the limits of our current knowledge. Are there hypergiants even larger than those we've discussed? Might unusual conditions in distant parts of the universe allow for stars that exceed the theoretical limits derived from our current understanding of stellar physics? The history of astronomy suggests humility about declaring absolute limits, as new discoveries have repeatedly expanded our conception of what's possible in the cosmos. At the same time, theoretical physics does suggest genuine constraints on stellar size. The Eddington limit, which balances gravity against radiation pressure, implies that stars above a certain luminosity cannot maintain stable structures. Similarly, the relationship between a star's mass, luminosity, and internal pressure suggests maximum sizes beyond which a coherent star cannot exist. These theoretical limits, combined with extensive observational searches, suggest that we've likely discovered stellar giants close to the maximum possible size. Stars like UY Scuti and Stephenson 2-18 probably represent the upper bound of what's physically possible for a single star under the laws governing our universe. This conclusion, if correct, gives these hypergiants additional significance. They aren't just very large stars, but representatives of the absolute maximum size a star can achieve. They stand at the boundary of stellar possibility, showing us the ultimate expression of the physical processes that create and maintain stars. In this sense, hypergiants tell us something fundamental about our universe, revealing the limits of certain forms of cosmic organization. Just as particle physics seeks the highest energies to probe the fundamental nature of matter, stellar astronomy looks to the most extreme stars to understand the limits of larger-scale cosmic structures. As our journey through the realm of stellar giants approaches its conclusion, we're left with a complex mixture of scientific understanding and philosophical wonder. Hypergiants represent both the extraordinary power of human science to comprehend the cosmos and the limitations of human intuition when confronting objects of truly cosmic scale. They remind us that we inhabit a universe of extremes, where physical processes explore the full range of what's possible under natural law, and they connect us, through the elements they create and disperse, to the grand narrative of cosmic evolution, the billions of years of stellar life and death that made our existence possible. In the final chapter, we'll draw together the threads of our exploration, reflecting on what the biggest stars in the universe reveal about cosmic processes and about our own relationship with the vast, dynamic cosmos we inhabit. Our journey through the realm of cosmic giants now draws to a close. We've explored the largest stars in the universe, those stellar behemoths that represent the maximum size a single object can achieve under the laws of physics. These stellar monsters, with diameters that could engulf much of our solar system, exist in a precarious balance between gravity pulling inward and radiation pushing outward. This delicate equilibrium cannot last, making hypergiants among the most short-lived objects in the cosmos, despite their tremendous size. Their brief lives and spectacular deaths play crucial roles in cosmic evolution. Through nuclear fusion and supernova explosions, hypergiants create and distribute the heavy elements necessary for planets and eventually life. The calcium in our bones, the iron in our blood, the oxygen we breathe, all had their origins in stars. Despite their importance, hypergiants remain exceptionally rare. Among hundreds of billions of stars in our Milky Way, Only a few hundred likely qualify as true hypergeans. Their formation requires special conditions, their stability is tenuous, and their lifespans are cosmically brief. The study of these stellar giants showcases the remarkable capabilities of modern astronomy. Without ever leaving our small planet, humans have managed to discover, measure, and understand objects trillions of kilometers away and billions of times larger than ourselves. At the same time, hypergiants remind us of the gap between intellectual understanding and intuitive comprehension. We can calculate that UY Scuti is approximately 1,700 times the diameter of our Sun, but truly grasping what this means remains challenging. As we contemplate the largest stars in the universe, we're confronted with questions of cosmic destiny. Hypergiants represent just one phase in the universe's evolution. They were absent in the very early cosmos and will eventually disappear as star formation ceases in the distant future. The night sky becomes more precious when viewed in this light. When we look up at visible supergiants like Betelgeuse or Antares, we're seeing objects that exist for just a cosmic moment, their light traveling to us across hundreds of light years. What emotions are appropriate when contemplating such objects? Awe at their scale? Humility at our physical insignificance? Wonder at the processes that create and destroy them? Perhaps satisfaction at our ability to understand them despite their remoteness? Most will experience some mixture of these reactions. The recognition of our physical smallness, alongside our intellectual reach, creates a complex emotional response with elements of both humility and wonder. The largest stars ever found may one day collapse into darkness, but for now, they burn, they roar, they watch. Their light travels across thousands of light years to reach our small planet, where beings of consciousness have learned to interpret this light, extracting knowledge of the stars themselves. Sleep now beneath the gentle shadow of a cosmic titan, knowing that even the greatest stars are governed by the same laws that shape our lives. The elements in your body were forged in stellar furnaces and scattered by stellar deaths. The hypergiant burns in distant space. You rest on a small planet, orbiting an ordinary star. Both exist according to the same physical laws. Both consist of matter born in the Big Bang and processed through generations of stars. Sleep now, beneath a sky shaped by stars bigger than worlds, knowing that in your understanding of these distant giants, the cosmos achieves one of its most remarkable feats, the comprehension of itself through the consciousness of its own matter, organized into the brief but brilliant configuration we call humanity.